What are the chances that two stellar bodies would burst into visibility for the unaided eye? That two powerful earthquakes would rip through Venezuelan geology, and that the notorious Three-Eye Atlas would be struck by a solar tempest all within a 72-hour window? If someone presented this as a screenplay, publishers would dismiss it as far too improbable for audiences to accept. Yet this is our actual world, and our world has just produced the most perfectly timed celestial spectacle in contemporary astronomical records. Following these recent occurrences, even the most skeptical thinkers are beginning to question whether we're observing something considerably more unusual than mere chance. This evening, we'll analyze each incident with meticulous detail, explore the mechanisms behind stellar outbursts and geological disturbances, then move into the uneasy space where random occurrence encounters pattern identification. Remain with me through to the conclusion, because our findings about September 2025 may shake our fundamental understanding of what's truly transpiring above us. Two stellar bodies detonate. Two massive seismic events fracture the terrain beneath Venezuela, and an interstellar traveler receives a glancing blow from a coronal mass ejection. All of this unfolds within a matter of days during late September 2025. If you're beginning to sense that the cosmos is attempting to communicate something to us, you're certainly not the only one. Let's chart this celestial convergence of incidents with exactness. On the 23rd of September, astronomers identified V1935 Centauri, a nova that ignited in the southern constellation Centaurus, intensifying to unaided eye visibility at magnitude 5.8 within a matter of days. Another stellar detonation made itself known. V7994 Sagittarius blazed into existence in the Archer constellation at magnitude 6.2. Two stellar bodies, both abruptly visible to anyone prepared to venture outside and gaze upward. Meanwhile, 7,000 miles distant from the closest observatory, Earth itself was generating news. At 22:21 UTC on the 24th of September, a magnitude 6.2 earthquake struck 24 kilometers east-northeast of Mexique in Venezuela's Zulia state. The tremor, originating merely 7.8 kilometers beneath the surface, transmitted shock waves throughout both Venezuela and Colombia. Yet nature had not concluded its display. Hours afterward, at 3:51 UTC on the 25th of September, a second quake, magnitude 6.3, ruptured the identical region. This occurrence originated from 14 kilometers down. Twin stellar bodies, twin seismic events, and overhead, imperceptible to the unaided eye, yet monitored by satellites. Something additional was developing. Solar weather forecasters at NOAA Space Weather Prediction Center were observing coronal mass ejections, billion-ton formations of magnetized plasma, launched from the sun at velocities surpassing 1 million miles per hour. Their computational models indicated these solar tempests were intersecting trajectories with something extraordinary: Three-Eye Atlas, the third verified interstellar visitor to our solar neighborhood. This is the point where the chronology becomes almost dramatically synchronized. The nova identifications and Venezuelan seismic events clustered around September 23rd through 25th. CME prediction models displayed maximum activity throughout the same time frame. And Three-Eye Atlas, identified merely 2 months prior by the Asteroid Terrestrial Impact Last Alert System, was navigating the inner solar system during what may prove to be the most energetic period of Solar Cycle 25. The geographical distribution of these incidents spans dimensions that defy human comprehension. The novae erupted in Centaurus and Sagittarius constellations, observable chiefly from Earth's southern hemisphere. Their radiation, having journeyed thousands of years to contact us, arrived precisely during this extraordinary week. The earthquake struck near Mexique in northwestern Venezuela, in a tectonically intricate region where the Caribbean and South American plates grind against one another. The coronal mass ejection spread through the inner heliosphere, a spatial volume exceeding Jupiter's orbit. And 3I Atlas was traversing the ecliptic plane, the conceptual disk where most planetary phenomena occur, threading between Mars and the Sun. We're not asserting a causal relationship here. That would be hasty, potentially irresponsible. What we're accomplishing is charting the cluster, recording the convergence, and preparing to evaluate mainstream scientific interpretations against more speculative hypotheses. The United States Geological Survey affirms no established link between space weather and seismic activity. Solar physicists would inform you that coronal mass ejections are standard features of an active sun. Stellar astronomers regard novae as foreseeable if unpredictable outcomes of binary star development. However, here's what renders this week genuinely unprecedented in contemporary astronomical history. 3I Atlas constitutes only the third confirmed interstellar object ever identified, following Oumuamua in 2017 and Borisov in 2019. More intriguingly, this marks the first occasion we may observe an interstellar visitor subjected to intense solar weather near solar maximum. We possess precedent for what CMEs can accomplish to solar system comets. In 2007, the European Space Agency's stereo satellites recorded a coronal mass ejection, literally severing the ion tail from Comet Encke disconnection incident that demonstrated the destructive reality of space weather encounters. The implications for the Chetians for the approaching months extend well beyond scholarly interest. 3I Atlas is scheduled for a Mars flyby on the 3rd of October, passing within 0.19 astronomical units, approximately 28 million kilometers of the red planet. Mars orbiters, including ESA ExoMars and NASA's Mars Reconnaissance Orbiter, are preparing opportunistic observations that could distinguish details of the interstellar visitor's nucleus in coma at unprecedented clarity. By late October, specifically the 29th, 3I Atlas reaches perihelion, its nearest approach to our Sun, at 1.36 astronomical units. Still exterior to Earth's orbit, yet near enough for ground-based telescopes to examine its composition and characteristics in real time. The viewing geometry becomes even more advantageous by the 19th of December, when 3I Atlas makes its nearest approach to Earth at 1.8 astronomical units. For perspective, that's nearer than Mars at its most remote, providing months of observation possibilities for both professional observatories and amateur astronomers equipped with modest telescopes. This convergence materializes during a season when space weather customarily intensifies. The autumn equinox activates what space physicists designate the Russell-McFerrin effect, a geometric peculiarity in Earth's magnetic field orientation that magnifies geomagnetic coupling with solar wind disturbances. September through November historically generate some of the year's most magnificent auroral exhibitions and most substantial space weather impacts on technology. Our commitment to you is this. We'll provide both rigorous scientific interpretations and daring what-if scenarios, but we'll distinguish each explicitly. You deserve to understand what's observationally verified versus what's scientifically conjectural versus what's frankly imaginative. The data is significant. The wonder is significant. And occasionally, the most truthful thing science can declare is, we don't know yet, but we're observing. Consider this inquiry as we delve deeper. If coronal mass ejections can strip the tails from comets that have circled our Sun for millennia, what might they inflict upon an object that spent millions of years traveling between the stars, transporting ice and dust formed in an entirely different stellar system? We're on the verge of discovering. Next, we'll scrutinize those sudden stellar detonations, the twin novae that illuminated southern skies precisely as Earth's crust began to convulse. in the pre-dawn hours of the 23rd of September, 2025. Amateur astronomer John Seach was performing what he's accomplished for decades, scanning the southern skies from his observatory in Chatsworth Island, New South Wales, searching for stellar detonations. What he discovered that morning would soon capture the attention of gamma-ray satellites and X-ray telescopes across the solar system. V1935. Centauri announced itself not with celebration, but with photons. Seach's initial identification revealed a star where no star had been sufficiently bright to notice previously. Situated in the constellation Centaurus, at magnitude 5.8 barely bright, enough for sharp-eyed observers in dark locations to detect without binoculars. Yet this was no ordinary brightening. Within hours of Seach's discovery report reaching the Central Bureau for Astronomical Telegrams, space-based observatories began identifying something remarkable. NASA's Fermi Gamma-Ray Space Telescope triggered on high-energy photons streaming from the nova's direction. The Swift Observatory, engineered to capture gamma-ray bursts, rotated its X-ray telescope toward Centaurus and commenced recording hard X-ray emission signatures of violent particle acceleration in the nova's expanding shock wave. These weren't merely attractive lights for backyard stargazers. This was evidence of physics operating at extremes. Electrons and protons accelerated to near-light velocities. Magnetic fields twisted into knots, temperatures climbing into the millions of degrees. But V1935 Centauri wasn't finished generating headlines. Merely days afterward, Seach struck again, or rather the cosmos did. V7994 Sagittarius erupted in the neighboring constellation Sagittarius, achieving magnitude 6.2 at discovery. 2 stellar detonations, both credited to the same observer, both bright enough for small telescopes or binoculars, both occurring within the same remarkable week. Here's why this pair caught professional astronomers by surprise. While novae aren't exceptionally uncommon, perhaps 10 to 12 occur in our galaxy each year. Having 2 reach near naked eye brightness within days is genuinely unusual. The previous occasion observers enjoyed 2 bright novae simultaneously was during the summer of 2023, and prior to that, you'd need to reach back several years to find comparable displays. The physics underlying these eruptions tells a narrative of stellar cannibalism enacted over cosmic time. Each nova begins with a white dwarf, the dense, hot core of a deceased star, roughly Earth-sized, but with our sun's mass. This stellar remnant sits in orbit with a normal star, gradually stealing hydrogen from its companion's outer atmosphere. For years, centuries, or millennia, gas accumulates on the white dwarf's surface, growing denser and hotter under the immense gravitational compression. Eventually, temperature and pressure reach a critical threshold. The accumulated hydrogen undergoes runaway thermonuclear fusion, not the controlled burning that powers living stars, but an explosive conflagration that can brighten the binary system by factors of 10,000 or more. The explosion doesn't destroy the white dwarf. Instead, it expels the surface layer, returning the system to its patient process of accumulation. Some novae recur on predictable timescales, erupting every few decades. Others may wait thousands of years between outbursts. V1935, Centauri's gamma-ray and hard X-ray signatures reveal the nova's most violent aspects. When the thermonuclear explosion launches material outward at speeds of thousands of kilometers per second, it creates shocks that accelerate particles to enormous energies. These relativistic particles interact with magnetic fields and surrounding matter, producing the high-energy photons that triggered Fermi and Swift. It's the same physics that operates in supernova remnants and active galactic nuclei cosmic particle accelerators that transform ordinary matter into high-energy radiation. 4. Observers in Earth's southern hemisphere. Both novae occupy prime viewing territory. V1935 Centauri sits well south of the celestial equator, making it a challenging target for northern observers who must wait for it to rise above their southern horizon. V7994 Sagittarius, located in the Archer constellation, presents similarly southern viewing, geometry appearing low in the south for mid-northern latitude observers, but riding high in the sky for anyone south of the equator. The discovery process itself reveals the collaborative nature of modern transient astronomy. Sitch's initial observations, reported through the International Astronomical Union's Central Bureau, triggered a cascade of follow-up observations. Circular number 5611 confirmed V1935 Centauri's detection, while 5612 documented V7994 Sagittarius. Within days, observatories around the world were obtaining photometry precise brightness measurements and spectroscopy that revealed the characteristic emission lines of hydrogen, helium, and heavier elements in the expanding nova shells. Amateur astronomers play crucial roles in nova science through organizations like the American Association of Variable Star Observers. Their nightly monitoring provides the temporal resolution that reveals how nova light curves evolve the complex patterns of brightening, plateau phases, and gradual decline. They contain clues about the explosion physics and the binary system's properties. Professional telescopes can't monitor every nova continuously, but dedicated amateurs can track brightness changes night after night, contributing data that shapes our understanding of these stellar explosions. The naming convention often confuses newcomers to astronomy. V1935 Centauri received its designation as the 1935th variable star, officially named in the Centaurus constellation, while V7994 Sagittarius became the 7994th in Sagittarius. These permanent names replace the temporary designations assigned at discovery, which can sometimes make the timeline appear confusing when later discovered objects receive earlier numbers due to administrative processing delays. Both novae are expected to fade over the coming weeks and months. Following the typical nova decline, they can span months to years. However, their evolution may include surprises. Some novae develop dust formation episodes weeks after eruption, temporarily dimming as newly formed dust grains absorb and scatter the nova's light. Others show complex multi-peaked light curves as different physical processes dominate at different times. The question that space weather enthusiasts can't help asking is whether these stellar explosions, occurring during the same week as significant geomagnetic activity, represent more than coincidence. The mainstream astronomical answer is clear. Novae in neighboring constellations, located thousands of light years from Earth, pose no direct threat to our planet and exert no measurable influence on terrestrial phenomena. The energy from these explosions, while enormous by human standards, dissipates across the vast distances of interstellar space, arriving at Earth as a gentle increase in photons, beautiful to observe, harmless to experience, yet the timing feels remarkable. Twin stellar explosions during a week of twin earthquakes, with an interstellar visitor threading through active solar weather. Perhaps the most honest response is to acknowledge both the science and the synchronicity, to appreciate the physics while remaining open to the possibility that our universe occasionally arranges itself in ways that stretch coincidence towards something approaching poetry. Meanwhile, 7,000 miles from any observatory capable of detecting these stellar fireworks, the solid Earth beneath Venezuela was about to demonstrate that explosions weren't limited to distant suns at precisely 22 hours, 21 minutes, and 55 seconds Coordinated Universal Time on the 24th of September. The Earth's crust beneath Venezuela's Zulia state released energy equivalent to several nuclear weapons. The magnitude 6.2 earthquake struck 24 kilometers east-northeast of Mexique, originating from a relatively shallow depth of 7.8 kilometers close, enough to the surface to shake buildings across two nations. The seismic waves propagated outward at roughly 6 kilometers per second through the rock, reaching populated areas within seconds of the rupture. From Maracaibo to Caracas, from Colombian border towns to Caribbean coastal cities, millions of people felt the ground sway beneath their feet. Social media erupted with videos of swinging chandeliers, rattling windows, and residents evacuating buildings as emergency protocols kicked into action across the region. But the Earth wasn't finished. Just 5.5 hours later, at 03 hours 51 minutes and 39 seconds UTC on the 25th of September, a second major rupture struck virtually the same location. This time, the magnitude 6.3 earthquake originated from 14 kilometers depth deeper than its predecessor, but still shallow enough to generate intense surface shaking. The epicenter sat approximately 27 to 28 kilometers east-northeast of Mexique, overlapping the first event's rupture zone. To understand why these twin quakes matter, we need to grasp the logarithmic nature of earthquake magnitude scales. A magnitude 6.3 earthquake releases approximately twice the energy of a magnitude 6.2 event. Combined, these two ruptures produced energy equivalent to a single magnitude 6.4 to 6.5 earthquake, a significant release even by global standards. The September 24th and 25th events represented the largest seismic activity in the region since the magnitude 7.8 Kamchatka earthquake on the 18th of September, placing Venezuela's twin quakes among the most notable global seismic events of late. September 2025, the aftershock sequence provided its own drama. A magnitude 5.8 earthquake struck the same region later on the 25th of September UTC, following the typical Omori decay pattern that seismologists expect after major ruptures. While 5.8 might sound modest compared to the main shocks, it's still large enough to cause additional damage, maintain anxiety levels among regional populations already stressed by two major events. Regional tectonics explain why this area generates such powerful earthquakes. The Maracaibo Basin sits within a complex zone where the Caribbean plate grinds against the South American plate, creating a network of fault systems, including the Bacono fault system and the Oca-Ancon-Santa Marta fault trends. These geological boundaries have been accumulating stress for years, decades or centuries, storing energy that eventually must be released through sudden slip events, earthquakes. Depth difference between the two main events to 7.8 kilometers versus 14 kilometers matters significantly for ground shaking intensity. Shallow earthquakes typically produce stronger surface acceleration than deeper events of the same magnitude because seismic waves have less opportunity to spread out and weaken during their journey to the surface. The September 24th event's shallow depth likely contributed to the widespread reports of strong shaking across both Venezuela and Colombia. Different seismological agencies reported slightly varying magnitudes for these events, reflecting the complexities of earthquake measurement. The United States Geological Survey initially reported the first earthquake at magnitude 6.2, while the European Mediterranean Seismological Center and other international monitoring networks provided measurements ranging from 6.1 to 6.3. These differences arise from various factors. Different measurement methodologies, updates as additional seismic station data becomes available, and distinctions between moment magnitude, surface wave magnitude, and body wave magnitude calculations. The human impact of these earthquakes extended far beyond seismological statistics. Evacuation orders affected thousands of residents, particularly in multi-story buildings that experienced prolonged swaying during the events. Emergency response teams mobilized across the region, conducting damage assessments and ensuring that critical infrastructure hospitals, bridges, power plants remained operational. While initial reports suggested relatively limited structural damage, given the earthquake's magnitudes, assessment teams continued their work for days after the events, documenting both visible damage and potential longer-term structural weakening. Historically, this region has experienced significant seismic activity. The complex tectonics around Lake Maracaibo and the broader Korean-South American plate boundary generate regular earthquake sequences. Though events of this magnitude occur regularly, the geological record reveals that major ruptures in this region can sometimes trigger additional activity on nearby fault segments, a process called stress transfer that occurs when one earthquake changes the stress field on adjacent fault systems. The timing raised questions among both professional seismologists and the public. Could additional large earthquakes follow? The statistical answer is nuanced. Aftershock sequences are expected and normal, with the largest aftershocks typically occurring within days to weeks of the main shock. However, seismologists cannot reliably predict whether an even larger earthquake might occur in the same region in the short term. The science of earthquake prediction remains elusive, despite decades of research into precursory phenomena, stress accumulation patterns, and statistical forecasting methods. International monitoring networks tracked every aftershock, building a picture of how the fault system was responding to the stress changes created by the two major ruptures. The Global Centroid Moment Tensor Database began processing detailed analyses of the fault orientations, slip directions, and rupture mechanisms for both events, information that helped seismologists understand which fault segments actually moved and how the stress field changed across the broader region. 4. Residents of Zulia State and neighboring areas. The twin earthquakes represented a stark reminder of their region's geological reality. Building codes, emergency preparedness, and community response systems all faced testing during such events. The relatively moderate damage reports, given the earthquake's magnitudes, likely reflect both fortunate timing. The events occurred during hours when many people were at home rather than in potentially vulnerable workplaces, and ongoing improvements in construction standards and emergency response capabilities. The broader question that emerged from these events involves their timing relative to other phenomena occurring during the same remarkable week. Seismologists maintain that no demonstrated physical mechanism connects solar activity, space weather, or astronomical events to earthquake occurrence. The United States Geological Survey's official position emphasizes that correlations between space weather and seismic activity remain unproven despite periodic claims in both scientific literature and popular media. Yet the human mind naturally seeks patterns, especially when dramatic events cluster in time. Twin novae, twin earthquakes, active solar weather, and an interstellar visitor threading through the inner solar system. The convergence feels significant even if the mechanisms remain unclear. Perhaps the most scientifically honest approach is to document the timeline, understand each phenomenon independently, and remain open to discovering connections while avoiding the temptation to assume causation where only correlation appears. As aftershocks continue to rattle Venezuela's consciousness, the sun was preparing to demonstrate that Earth's immediate neighborhood could be every bit as dynamic as its solid surface, 93 million miles above Venezuela's shaking ground. Our star was conducting its own explosive symphony. During the same days that stellar explosions illuminated southern skies and earthquakes ruptured South American bedrock, the sun unleashed coronal mass ejections, billion-ton clouds of magnetized plasma that would cross paths with something unprecedented in human experience. An interstellar visitor. Coronal mass ejections represent some of the most powerful events in our solar system. These eruptions begin in the sun's corona, where magnetic field lines twist, tangle, and eventually snap like overstressed rubber bands. When magnetic reconnection occurs, it releases energy equivalent to billions of hydrogen bombs, accelerating plasma to speeds between 250 and 3,000 kilometers per second, fast enough to traverse the Earth-Sun distance in 1 to 4 days. NASA's Space Weather Prediction Center tracks these solar storms using the WSAN-LEO model, a sophisticated computer simulation that maps how coronal mass ejections propagate through the heliosphere. The model considers solar wind speed, density, and magnetic field orientation to forecast when and where these plasma clouds will intersect spacecraft, planets, and other objects in their path. During late September 2025, NLEO forecasts showed active conditions multiple CME events threading through the inner solar system during the same days. That brought us twin novae and twin earthquakes. But here's where this story becomes historically unique. For the first time in recorded human experience, one of these solar storms was on a collision course with an object born in another star system. 3I Atlas, discovered just 2 months earlier by the Asteroid Terrestrial Impact Last Alert System, was threading through the inner heliosphere during some of Solar Cycle 25's most active conditions. The interstellar visitor, following a retrograde trajectory, inclined roughly 175 degrees to the ecliptic plane, was crossing the same region of space where Earth orbits prime real estate for encountering solar weather phenomena. We have precedent for what happens when coronal mass ejections collide with comets. The interaction isn't subtle speculation. It's documented physics, captured by spacecraft cameras, and analyzed in peer-reviewed literature. In 2007, the European Space Agency's stereo satellites filmed a CME, completely severing the ion tail of Comet Encke. The disconnection event, lasting several hours, demonstrated the violent reality of magnetic reconnection between solar plasma and cometary material. Comet tails form through 2 distinct processes, each responding differently to solar influence. Dust tails curve gracefully away from the sun, pushed by radiation pressure, the gentle but persistent force of sunlight striking microscopic particles. Ion tails, by contrast, stretch straight away from our star, following magnetic field lines embedded in the solar wind. When a coronal mass ejection disrupts these magnetic connections, ion tails can disconnect entirely, drift away from the comet, and eventually dissipate while new tails form from fresh material. The claim that 3I Atlas was sideswiped by a CME rests on model-based trajectory analysis rather than direct observation. ENLIL forecasts suggested that solar storm paths would intersect the interstellar visitor's position during late September, but we must maintain transparency about uncertainty. Space weather models excel at predicting general trends, but struggle with fine details. The interaction remains a forecast inference rather than a peer-reviewed detection. If the interaction occurred as models suggested, we might expect several observable consequences. Increased ionization could brighten the interstellar visitor's coma, the fuzzy atmosphere of gas and dust surrounding its nucleus. Changes in ion tail morphology might appear in telescopic images as magnetic field disruptions, alter how charged particles stream away from the object. Spectroscopic observations could reveal chemical signatures as solar energy liberates specific molecules like CN, CO, and CO from the visitor's ancient ice. Amateur astronomers worldwide were positioned to document any such changes. The global network of comet observers, connected through online forums and observing organizations, maintains nightly vigils on interesting objects. Their images, when compared across time, reveal subtle changes in brightness, tail structure, and coma morphology that often escape detection by professional observatories focused on other targets. The physics of CME-comet interactions involves magnetic reconnection, the same process that triggers solar flares and geomagnetic storms. When solar plasma carrying tangled magnetic field lines encounters a comet's ionosphere, field lines can connect, disconnect, and reconnect, releasing energy that accelerates particles and generates observable phenomena. It's elegant physics, magnetic field topology changing in real time, converting stored magnetic energy into kinetic energy of charged particles. 3I Atlas represents more than just another target for solar weather interactions. As the third confirmed interstellar object after Oumuamua in 2017 and Borisov in 2019, it carries material formed around a different star in a different stellar system, potentially billions of years ago. If solar storms can alter its behavior, we're witnessing the first documented case of our sun directly interacting with matter from another stellar neighborhood. Visitors' geometry makes these interactions more likely than they were for previous interstellar objects. Unlike Oumuamua, which passed through the inner solar system quickly and at high inclination to the ecliptic plane, 3I Atlas follows a trajectory that keeps it near the high ecliptic, the plane where solar activity tends to concentrate, and where Earth experiences most space weather effects. Solar Cycle 25 has provided an active backdrop for these interactions. The 11-year solar cycle reached its current maximum phase during 2024 and 2025, producing elevated sunspot numbers, increased flare frequency, and more frequent coronal mass ejections. The cycle's timing means 3I Atlas is experiencing our star at its most temperamental, subjected to space weather conditions that previous interstellar visitors missed. Observational verification of CME interactions requires careful analysis of brightness changes, spectroscopic variations, and morphological evolution over timescales of hours to days. Professional observatories and amateur astronomers worldwide were monitoring 3I Atlas throughout late September, though initial results remained preliminary as analysis continued. The larger implications extend beyond this single event. If we can document how our sun influences interstellar material, we gain insights into similar processes throughout the galaxy. Other star systems presumably launch their own coronal mass ejections, potentially altering interstellar objects that pass through their neighborhoods. 3I Atlas might carry signatures of interactions with previous stellar systems encountered during its million-year journey through space. As September 2025 drew to a close, the convergence of events, stellar explosions, terrestrial earthquakes, solar storms, and interstellar visitor interactions created a timeline that challenged comfortable assumptions about cosmic coincidences. Were we witnessing unrelated phenomena clustering by chance, or was something more systematic at work? The answer would emerge as 3I Atlas continued its journey toward a Mars flyby on the 3rd of October, carrying whatever modifications our sun's coronal mass ejections might have imposed on this traveler from the stars. Step back for a moment and consider what we've mapped. Twin stellar explosions visible to the naked eye. Twin magnitude 6 earthquakes rupturing within hours of each other. Coronal mass ejections threading through the inner solar system. And an interstellar visitor crossing our neighborhood during solar maximum conditions. A lot of universe happening very fast, compressed into the final week of September 2025. This is where honest science meets human pattern recognition, and the collision isn't always comfortable. Our brains evolved to detect meaningful connections in complex environments. The rustle that might signal a predator. The cloud formation that could bring rain. The behavioral changes that might indicate social threat or opportunity. This cognitive architecture serves us well in many contexts. But it can also lead us to perceive significance in coincidental clustering. The scientific mainstream offers clear guidance on these events. The United States Geological Survey has found no verified link between space weather events and seismic activity. Numerous correlation studies conducted over decades have consistently failed to identify dependable predictive connections between solar phenomena and earthquakes. Professional seismologists stress that predicting earthquakes remains scientifically impossible with current methods, regardless of whether those methods rely on terrestrial warning signs or extraterrestrial factors. In a similar vein, stellar astronomers regard novae as expected outcomes of binary star dynamics that occur when white dwarf stars gather enough matter from their companion stars to initiate thermonuclear runaway reactions. Nova eruption timing is governed by stellar physics rather than influences from Earth or elsewhere in our solar system. V1935 Centauri and V7994 Sagittarius exemplify standard, albeit visually striking, instances of phenomena that unfold regularly throughout our galaxy. Solar physicists examine coronal mass ejections as natural byproducts of magnetic field changes within the Sun's corona. These phenomena happen more often during periods of solar maximum, which makes late 2025 a statistically probable time for numerous CME occurrences. The interplay between solar storms and cometary matter has been thoroughly documented, representing well-understood plasma physics rather than unusual phenomena. Nevertheless, recognizing mainstream scientific perspectives doesn't demand we disregard the extraordinary nature of this temporal clustering. Occasionally, the universe organizes itself in patterns that push coincidence towards something resembling synchronicity. Even when the fundamental mechanisms remain ordinary, the question emerges: how do we create space for both strict skepticism and genuine wonder? Our methodology throughout this investigation will establish distinct boundaries between various categories of assertions. Observational data magnitude readings, positional coordinates, spectroscopic findings constitute our foundation. These represent what instruments captured, what satellites identified, what seismographs recorded. Upon this foundation, we'll construct layers of scientific analysis grounded in established physics and thoroughly validated models. Beyond proven science exists the domain of conjecture, which we'll explore cautiously and with transparent labeling. Speculative correlations, potential relationships between solar activity and terrestrial events, possible influences of stellar phenomena on solar system behavior, theoretical mechanisms connecting cosmic and geological processes all merit investigation. Assuming we maintain clarity about their standing as hypotheses rather than established facts. The terminology of cosmic phenomena requires clarification for general readership. A nova constitutes a stellar explosion that intensifies a binary star system by factors ranging from thousands to millions, triggered by thermonuclear runaway reactions on a white dwarf surface. It differs fundamentally from a supernova, which completely annihilates the exploding star. A coronal mass ejection comprises billion-ton plasma clouds expelled from the Sun at velocities ranging from hundreds to thousands of kilometers per second. Perihelion designates an object's nearest point to the Sun along its orbital path. An astronomical unit equals the mean distance between Earth and the Sun, approximately 93 million miles or 150 million kilometers. Ion tails develop when solar wind removes electrons from gas molecules within a comet's coma, producing charged particles that trace magnetic field lines extending directly away from the Sun. These tails can stretch millions of kilometers through space, offering visible proof of invisible magnetic dynamics operating between stars and smaller celestial bodies. What follows in our examination will distinguish observed events from imagined associations while honoring both scientific precision and human inquisitiveness. We'll investigate the intricate physics underlying stellar explosions, earthquake ruptures, and solar storm dynamics. We'll monitor 3I Atlas throughout its Mars flyby on October 3rd and perihelion passage on October 29th. We'll explore legitimate scientific theories about connections between cosmic and terrestrial occurrences alongside explicitly marked speculation regarding more unconventional possibilities. The autumn equinox season customarily intensifies space weather phenomena through the Russell-McLaren effect, a geometric interaction between Earth's magnetic field and solar wind conditions that frequently strengthens geomagnetic activity throughout September and October. This seasonal amplification adds further context for why late September might generate heightened space weather activity independent of any correlation with other events. 3I Atlas presents exceptional scientific prospects, precisely because it represents our third confirmed interstellar visitor and the first observed under highly active solar conditions. The geometry of its path, passing near the ecliptic plane where most solar system activity concentrates, maximizes opportunities for multi-mission observations and space weather interactions. Unlike Oumuamua, which departed swiftly before thorough investigation, or Borisov, which maintained relatively substantial distance, 3I Atlas provides prolonged observation windows spanning multiple months. The implications for October and November reach beyond purely academic curiosity. Mars orbiter missions, including ESA's ExoMars Tracegas Orbiter and NASA's Mars Reconnaissance Orbiter, have scheduled opportunistic observations during the October 3rd flyby, potentially yielding unprecedented high-resolution imagery of an interstellar visitor's nucleus and coma architecture. Ground-based observatories across the globe continue tracking brightness fluctuations, spectroscopic changes, and structural variations that might reveal how solar weather influences interstellar material. Regarding earthquake monitoring in Venezuela, aftershock patterns typically persist for weeks to months after major ruptures. While seismologists cannot forecast whether more powerful events might transpire, they sustain continuous surveillance of regional seismic activity and stress field development. The intricate tectonics characterizing the Korean South American plate boundary ensure this region will continue producing earthquakes, though their timing remains inherently unpredictable. Our dedication involves presenting multiple viewpoints honestly. Mainstream scientific explanations warrant primary consideration because they rest upon established physics and comprehensive observational evidence. Speculative theories deserve attention, provided they remain clearly differentiated from validated science. The human inclination to discover meaning in apparent patterns deserves acknowledgement, even when scientific evidence fails to support causative links. Perhaps the most striking dimension of this convergence involves its timing. We exist during humanity's first generation, capable of detecting interstellar visitors, monitoring global seismic activity instantaneously, observing stellar explosions across the electromagnetic spectrum, and tracking space weather throughout the solar system. Earlier generations might have witnessed bright novae and experienced earthquake tremors, but they couldn't have connected these phenomena to solar storms and interstellar visitors because the technology enabling such connections didn't exist. We will separate what is documented from what is imagined, what is proven from what is conceivable, what is probable from what is merely possible. So, how do stars explode without destroying themselves entirely? The answer unveils physics operating at magnitudes that defy human intuition. Envision a white dwarf star, a sphere roughly Earth's diameter, yet containing our entire sun's mass. Its surface gravity compresses matter to densities approaching 1 million times that of water. Surface temperatures hover near 50,000 degrees Fahrenheit. This stellar remnant represents what persists after a sun-like star depletes its nuclear fuel, expels its outer layers, and collapses into a sphere of degenerate matter where atoms exist in conditions impossible under terrestrial circumstances. Now picture this cosmic furnace locked in orbital partnership with a normal star, perhaps a red giant whose outer atmosphere has expanded to enormous proportions through aging. Gravity from the white dwarf gradually extracts hydrogen from its companion's extended atmosphere, drawing gas across interstellar space in streams that spiral inward like water, circling a drain. This stolen material gathers on the white dwarf's surface, becoming progressively denser and hotter under relentless gravitational compression. For decades, centuries or millennia, hydrogen accumulates. Temperature and pressure climb steadily as additional material accumulates on the white dwarf surface. Unlike the regulated nuclear fusion transpiring in stellar cores, this process builds toward explosive discharge. When temperature attains roughly 100 million degrees Kelvin, thermonuclear runaway initiates. The explosion creating V1935 Centauri transpires in seconds. Runaway fusion consumes the accumulated hydrogen layer in a conflagration that discharges energy equivalent to our sun's complete output across thousands of years. But here lies the essential distinction from a supernova. The white dwarf itself endures. The explosion expels only the surface layer of accumulated material, leaving the underlying stellar remnant intact and prepared to restart the process. This explains why V1935, Centauri's high-energy signatures, attracted attention from space-based observatories worldwide. When NASA's Fermi Gamma Ray Space Telescope identified gamma rays from the nova's location, it was documenting evidence of particles accelerated to near-light velocities in the explosion shock fronts. The Swift Observatory's hard X-ray detections exposed electrons spiraling through magnetic fields at tremendous energies, generating synchrotron radiation across the electromagnetic spectrum. These high-energy phenomena transform novae from simple brightening events into cosmic particle accelerators. The expanding shell of ejected matter racing outward at velocities exceeding several thousand kilometers per second creates shock waves upon colliding with the sparse interstellar gas. These shocks operate like natural cyclotrons, employing magnetic field acceleration to propel protons and electrons to energies requiring massive terrestrial laboratories to replicate. The American Association of Variable Star Observers coordinates amateur contributions to nova science through standardized photometry protocols. Visual observers estimate brightness using comparison stars, while CCD cameras deliver precise magnitude measurements revealing subtle variations in the nova's light curve. These observations, contributed by hundreds of amateur astronomers globally, provide the temporal resolution that professional observatories, focused on numerous targets, cannot sustain for individual objects. V1935, Centauri's brightness evolution, follows patterns established through decades of nova research. The initial rise from invisibility to naked eye magnitude typically unfolds over days to weeks. Peak brightness may endure anywhere from days to months, depending on the white dwarf's mass, the accretion rate from its companion, and the composition of ejected material. The decline phase can extend across months or years, sometimes interrupted by secondary peaks as different physical processes dominate the nova's energy production. Spectroscopy exposes the nova's chemical signatures. Early spectra typically display broad emission lines of hydrogen, helium, and heavier elements moving at high velocities, evidence of the expanding ejecta. As the nova matures, these lines narrow and shift as the ejected material cools and decelerates. Eventually, forbidden lines emerge, transitions possible only in the extremely low-density environments of expanding nova shells, where atoms may experience hours or days between collisions. The distances to V1935 Centauri and V7994 Sagittarius remain uncertain, but likely exceed several thousand light years. This means the explosions we witnessed in September 2025 actually transpired millennia ago, when human civilization was just beginning to cultivate agriculture and establish permanent settlements. The light from these stellar explosions has traversed interstellar space longer than recorded human history, reaching Earth precisely during this remarkable week. Amateur astronomers can contribute meaningful observations using modest equipment. A digital single-lens reflex camera with a telephoto lens can capture both novae during their bright phases. Visual observers using binoculars or small telescopes can estimate magnitudes by comparing the novae to nearby stars of established brightness. More sophisticated observers with CCD cameras and photometric filters contribute precision data, supplementing professional observations. The naming convention for nova designations reflects astronomical tradition and administrative processing. V1935 Centauri received its permanent variable star designation as the 1935th officially catalogued variable in the Centaurus constellation. The V prefix denotes a variable star, an object whose brightness changes over time. This permanent designation supersedes temporary discovery names that might include the discoverer's surname, discovery date, or catalog numbers from various survey programs. Dust formation represents one of nova evolution's most fascinating aspects. Weeks to months following the initial explosion, some novae undergo dramatic dimming as newly formed dust grains condense in the cooling ejecta. These dust dip events can diminish a nova's brightness by several magnitudes as microscopic particles absorb and scatter the nova's light. Eventually, the dust either disperses or is destroyed by the nova's continuing radiation, allowing the underlying stellar remnant to become visible again. The energy scales involved in nova explosions dwarf human experience while remaining modest compared to supernova. A typical nova releases energy equivalent to our sun's total output across roughly 10,000 years, sufficient to power human civilization for billions of years at current consumption rates. Yet this represents merely a tiny fraction of the energy released in supernova explosions, which can outshine entire galaxies for weeks or months. Recurrent novae complicate the straightforward picture of singular explosive events. Some white dwarf systems undergo nova eruptions on relatively predictable timescales, every few decades for the most frequent repeaters. These systems may experience dozens of nova explosions over astronomical time, gradually accreting sufficient material to approach the Chandrasekhar mass limit, where the white dwarf itself would explode as a Type Ia supernova. Professional follow-up observations of both September novae continue across multiple electromagnetic wavelengths. Ground-based telescopes monitor optical brightness changes and spectroscopic evolution. Space-based observatories, including the Hubble Space Telescope, may obtain high-resolution images of the expanding nova shells. Radio telescopes can detect synchrotron emission from relativistic particles in the nova ejecta. The classification of V1935 Centauri and V7994 Sagittarius as classical novae, rather than other types of stellar explosions, rests on spectroscopic evidence and brightness evolution patterns. Dwarf novae, caused by instabilities in accretion disks rather than thermonuclear explosions, typically exhibit different spectral characteristics and smaller amplitude brightenings. Luminous red novae, possibly caused by stellar mergers, display different colors and evolution timescales. Could either of these novae represent something more exotic than standard thermonuclear explosions? Current observational evidence supports classical nova interpretations, but astronomy maintains healthy skepticism regarding initial classifications. As more data accumulates from multi-wavelength observations, the detailed physics may reveal subtleties that refine our understanding of these particular explosions. The gamma-ray detection from V1935 Centauri places it among an emerging class of gamma-ray novae that challenge traditional models of nova physics. These high-energy emissions suggest particle acceleration processes, operating more efficiently than previously considered possible in nova environments. The physics may involve magnetic field reconnection, shock acceleration, or other mechanisms bridging the gap between nova explosions and more energetic phenomena like supernova remnants. As we track these stellar explosions across the electromagnetic spectrum, Earth's solid surface was preparing to demonstrate that our planet's interior remains every bit as dynamic as distant stars beneath Lake Maracaibo and the surrounding Zulia state of Venezuela lies one of South America's most tectonically complex regions. The Caribbean plate grinds against the South American plate along a boundary zone encompassing multiple fault systems. The Bacono fault system running northeast-southwest through the Venezuelan Andes. The Oca-Ancon fault trending east-west along the Caribbean coast. And the Santa Marta fault extending into Colombia. These geological boundaries have accumulated stress for decades, storing energy that must eventually discharge through sudden slip events. The magnitude 6.2 earthquake at 22:21 UTC on September 24th commenced as a rupture along one of these fault segments, approximately 7.8 kilometers beneath the surface. At this relatively shallow depth, seismic waves had limited opportunity to dissipate and weaken during their journey to the surface, amplifying ground acceleration across an extensive region. The initial rupture likely extended several kilometers along the fault plane, with sudden displacement measured in meters releasing stress, accumulated over years or decades. Waves propagated outward from the rupture zone at roughly 6 kilometers per second through the surrounding rock. Primary waves compressional disturbances causing back and forth motion along their travel direction arrived first at seismograph stations throughout the region. Secondary waves followed, creating the side-to-side motion that typically inflicts the most structural damage. Surface waves, traveling more slowly, but often carrying the most destructive energy, produced the rolling motions that eyewitnesses described as lasting minutes in some locations. Just 5.5 hours later, at 3:51 UTC on September 25th, a second major rupture struck virtually the identical region. The magnitude 6.3 earthquake originated from 14 kilometers, depth deeper than its predecessor, but still shallow enough to generate intense surface shaking. This second event likely occurred on an adjacent fault segment, triggered by stress changes created by the first rupture. The physics of stress transfer explains why earthquakes frequently occur in clusters. When one fault segment suddenly slips, it alters the stress field on nearby fault segments. Some areas experience increased stress, making them more susceptible to rupture in the near future. Other areas experience stress relief, becoming temporarily less likely to generate earthquakes. The September 24th rupture apparently loaded stress onto the fault segment that failed 5.5 hours later. The magnitude difference between 6.2 and 6.3 earthquakes might appear trivial, but the logarithmic nature of the magnitude scale means the second event released approximately twice as much energy as the first. Combined, these twin ruptures produced energy equivalent to a single magnitude 6.4 to 6.5 earthquake, a significant release ranking among the largest global seismic events of late September 2025. International seismological agencies reported slightly different magnitudes for these events, reflecting the complexities of earthquake measurement. The United States Geological Survey employs moment magnitude calculated from the total energy released during rupture. The European Mediterranean Seismological Center may utilize different magnitude scales based on surface wave amplitudes or body wave characteristics. These methodological differences, combined with updates as additional seismograph data becomes available, Explain why headlines reported magnitude ranges from 6.1 to 6.3 for the first event. The aftershock sequence followed patterns seismologists have documented for decades. The magnitude 5.8 earthquake that struck later on September 25th represents a typical large aftershock, smaller than the main shock, but still significant enough to cause additional damage and concern. Omori's law, formulated in the early 1900s, describes how aftershock frequency decays over time following major earthquakes. The largest aftershocks typically occur within days of the main shock, with smaller events continuing for weeks, months, or even years. Human impact from these earthquakes extended across both Venezuela and Colombia. The relatively shallow depths amplified surface shaking, leading to evacuation orders for high-rise buildings in major cities. Social media filled with videos of swinging light fixtures, rattling windows, and people evacuating buildings as emergency protocols activated across the region. While initial damage reports remained limited given the earthquake's magnitudes, assessment teams spent days documenting both visible structural damage and potential longer-term weakening of buildings and infrastructure. The regional geology helps explain why this area generates such powerful earthquakes. The Maracaibo Basin formed through complex interactions between the Caribbean and South American plates, creating a network of fault systems that accommodate ongoing tectonic motion. Lake Maracaibo itself sits within a down-dropped block bounded by normal faults experiencing active deformation. The petroleum deposits making this region economically important formed in sedimentary basins created by the same tectonic processes, generating earthquakes. Depth measurements carry significant uncertainty, especially for earthquakes occurring in geologically complex regions. The 7.8-kilometer depth reported for the first event and 14-kilometer depth for the second represent best estimates based on seismic wave arrival times and multiple monitoring stations. These depths place both earthquakes in the upper crust, where brittle fracture dominates over the ductile deformation, occurring at greater depths where temperature and pressure increase. The timing of these events raised questions about potential triggers. Could solar activity, atmospheric pressure changes, or other external factors influence earthquake occurrence? The scientific consensus, supported by the United States Geological Survey and international seismological organizations, maintains that no reliable correlation exists between space weather and earthquake activity. Decades of statistical analysis have failed to establish predictive relationships between solar flares, coronal mass ejections, geomagnetic storms, and seismic events. However, some research has explored more subtle potential connections. Changes in atmospheric pressure can alter stress on fault systems by minuscule amounts, typically far smaller than stress changes, caused by earth tides from lunar and solar gravitational effects. While these influences remain detectable with sensitive instruments, they fall orders of magnitude below the stress changes needed to trigger earthquakes on faults not already extremely close to failure. The Global Centroid Moment Tensor Database provides detailed analyses of fault orientations, slip directions, and rupture mechanisms for both Venezuelan earthquakes. These beach ball diagrams reveal which fault planes actually moved and in what directions, information helping seismologists understand regional stress fields and predict which fault segments might experience elevated risk in the future. Statistical seismology offers the only reliable approach to earthquake forecasting currently available. Following major earthquakes like those in Venezuela, the probability of additional large events in the same region increases, temporarily due to aftershock activity and stress transfer effects. However, this increased probability typically lasts weeks to months and cannot specify exactly when or where additional earthquakes might occur. Building codes and emergency preparedness systems face continuous testing in seismically active regions like Zulia's state. The relatively moderate damage reports following magnitude 6.2 and 6.3 earthquakes likely reflect both fortunate timing and ongoing improvements in construction standards. Modern seismic building codes require structures to withstand strong ground shaking, though older buildings may remain vulnerable to damage or collapse. Could larger earthquakes follow in the same region? The geological setting certainly permits more powerful events. The fault systems around Lake Maracaibo have generated magnitude 7 earthquakes historically, and the regional tectonics suggests such events will continue occurring irregularly over geological time. However, seismologists cannot predict whether days, years, or decades might pass before the next major rupture. The Venezuelan earthquake sequence demonstrates how solid Earth processes can produce dramatic energy releases over human timescales, while following physical laws operating over geological time. Stress accumulates slowly as tectonic plates grind past each other at rates of centimeters per year. When accumulated stress exceeds rock strength, sudden failure releases decades or centuries of stored energy in seconds to minutes of violent shaking. As aftershocks continued rattling the Caribbean-South American plate boundary, our attention turned to the space environment where another type of energy release was unfolding. At scales dwarfing terrestrial earthquakes, solar Cycle 25 reached its peak activity during 2024 and 2025, transforming our typically well-behaved star into a restless giant capable of hurling billion-ton plasma clouds across the solar system. On September 24th and 25th, as stellar explosions illuminated southern skies and earthquakes shook Venezuelan bedrock, solar activity indices painted a picture of a sun operating near maximum fury. The 10.7 centimeter radio flux, a key indicator of solar activity levels, hovered around 180 to 190 solar flux units during late September. This measurement, taken daily by radio telescopes, correlates strongly with the number and intensity of active regions on the sun's surface. Values exceeding 150 typically indicate elevated solar activity, while readings above 200 suggest very active conditions, capable of producing major space weather events. Sunspots themselves narrate the story of magnetic chaos unfolding in the sun's photosphere. These dark regions, often larger than Earth, form where powerful magnetic field lines penetrate the solar surface and suppress normal convective heat transport. The magnetic field strength in sunspot cores can exceed 3,000 Gauss, roughly 6,000 times, stronger than Earth's surface magnetic field. More sunspots generally mean more opportunities for magnetic field lines to tangle, reconnect, and explosively release energy as solar flares and coronal mass ejections. But raw sunspot numbers only hint at the complexity of solar maximum conditions. The sun's magnetic field during peak activity resembles a twisted, knotted tangle rather than the relatively simple dipole field dominating during solar minima. Active regions' collections of sunspots, connected by magnetic field loops, can persist for weeks or months, rotating across the solar disk and occasionally producing spectacular eruptions visible to spacecraft throughout the inner solar system. Coronal mass ejections represent the most dramatic manifestation of solar maximum physics. These events begin when magnetic field lines in the sun's corona become so twisted and stressed they suddenly snap and reconnect, converting magnetic energy into kinetic energy of charged particles. The process launches billion-ton plasma clouds into space at speeds ranging from 250 kilometers per second for slow events to over 3,000 kilometers per second for the fastest eruptions. An OA space weather prediction center tracks these solar storms using the WSA-Enlil model, a sophisticated computer simulation mapping CME propagation through the heliosphere. The model divides space into a three-dimensional grid extending from the sun to beyond Earth's orbit, calculating how solar wind speed, density, and magnetic field orientation evolve as plasma clouds travel through the solar system. While ENLO excels at predicting general arrival times and intensities, it cannot capture every detail of CME structure and behavior. The autumn equinox season traditionally amplifies space weather effects through a phenomenon as the Russell-McLaren effect. This geometric coupling arises from the orientation of Earth's magnetic field relative to the interplanetary magnetic field carried by the solar wind. During equinox periods, the geometry favors magnetic reconnection between solar wind magnetic fields and Earth's magnetosphere, often producing intense geomagnetic storms, even from relatively modest solar disturbances. Space weather impacts extend far beyond the aurora displays, capturing public attention. Geomagnetic storms can disrupt high-frequency radio communications used by aviation and maritime industries, force satellite operators to adjust spacecraft orbits due to increased atmospheric drag, and in extreme cases, threaten power grid stability through induced electrical currents. NOAA maintains scales for geomagnetic storms, G-scale, solar radiation storms, S-scale, and radio blackouts, R-scale, that help various industries prepare for and respond to space weather effects. Interaction between coronal mass ejections and comets provides a natural laboratory for studying plasma physics under conditions impossible to recreate on Earth. Ion tails form when solar wind strips electrons from gas molecules in a comet's coma, creating charged particles that follow magnetic field lines extending directly away from the sun. These tails can stretch millions of kilometers through space, providing visible evidence of invisible magnetic processes operating between our star and smaller bodies in the solar system. When a CME encounters a comet, the interaction can be dramatic and visually spectacular. The European Space Agency's STEREO satellites documented such an event in 2007 when a coronal mass ejection completely severed comet Encke's ion tail through magnetic reconnection processes. The disconnected tail drifted away from the comet over several hours while a new tail formed from fresh material, demonstrating the dynamic nature of space weather interactions. Solar maximum conditions during 2025 provided an active backdrop for 3I Atlas as it approached the inner solar system. Unlike previous interstellar visitors encountering our Sun during quieter solar cycle periods, this object experienced space weather effects near peak intensity. The combination of elevated CME frequency and the visitor's trajectory through the ecliptic plane, where most solar system activity concentrates, maximize the probability of significant interactions. The physics of CME propagation involves complex magnetohydrodynamics operating over scales from individual particle motions to structures larger than planetary orbits. Fast CMEs can overtake slower solar wind, creating compression regions and shock fronts that accelerate particles to high energies. Multiple CMEs can interact with each other, merging into larger, more powerful disturbances or creating complex magnetic field configurations that enhance particle acceleration and magnetic RECONNECTION. Professional space weather forecasters monitor multiple data sources to track solar activity and predict Earth impacts. The Solar Dynamics Observatory provides continuous high-resolution images of the sun's surface and corona in multiple wavelengths of extreme ultraviolet light. The Solar and Heliospheric Observatory watches for CMEs erupting from the sun's far side. The Advanced Composition Explorer, positioned between Earth and the sun, provides advance warning of incoming solar wind disturbances. Amateur radio operators serve as an informal global network for monitoring space weather effects on Earth. High-frequency radio propagation changes dramatically during geomagnetic storms. sometimes improving long-distance communications through enhanced ionospheric reflection, while degrading others through increased absorption and scattering. These real-time reports complement formal measurements from professional monitoring stations. The current solar maximum appears to be following a double-peaked pattern seen in some previous cycles, with initial peak activity during 2024, followed by continued high activity through 2025. This extended maximum phase means elevated space weather risks may persist longer than typical 11-year cycles, maintaining conditions favorable for dramatic solar-terrestrial interactions well into 2026. Aurora photography and observation have become increasingly popular during the current solar maximum, with social media filled with spectacular images of green, red, and purple lights dancing across polar and subpolar skies. These displays result from charged particles from solar storms interacting with Earth's upper atmosphere, exciting oxygen and nitrogen atoms that emit characteristic colors when they return to ground states. The solar wind itself carries embedded magnetic fields that originated in the sun's corona and stretched across the solar system as plasma flows outward. These interplanetary magnetic field lines connect planets, comets, and spacecraft in a vast web of electromagnetic influence extending to the heliopause, the boundary where solar wind pressure balances interstellar medium pressure, roughly 100 times farther from the Sun than Earth. As we tracked solar storms propagating through the inner heliosphere during late September 2025, one particular target captured the attention of space weather forecasters and astronomy enthusiasts alike. An interstellar visitor threading through this cosmic storm system on approach to its first encounter with another world. In the early morning hours of July 1, 2025, the Asteroid Terrestrial Impact Last Alert System telescope array detected something extraordinary moving against the background stars. Initial observations suggested a faint comet-like object, but orbital calculations quickly revealed its true nature. 3I Atlas, only the third confirmed interstellar visitor in human history, following the mysterious Oumuamua in 2017 and comet Orizov in 2019. The designation tells the story of its discovery and significance. The 3I prefix indicates the third interstellar object catalogued by the International Astronomical Union, while Atlas credits the telescope system that first spotted this cosmic wanderer. Unlike its predecessors, 3I Atlas arrived during a uniquely favorable observation window, bright enough for detailed study, following a trajectory, keeping it near the ecliptic plane where most solar system activity concentrates, and approaching during solar maximum conditions, offering unprecedented opportunities to study how our star influences interstellar material. The visitor's orbital characteristics reveal its alien origins. Its trajectory displays a hyperbolic shape with an eccentricity significantly greater than 1, indicating it possesses more than enough speed to escape the Sun's gravitational influence. The orbital inclination of approximately 175 degrees means 3I Atlas moves in a retrograde direction relative to the planet's backward compared to the normal flow of solar system traffic. Current models suggest the object measures somewhere between several hundred meters and possibly up to 1.5 kilometers across, though these size estimates carry substantial uncertainty. Direct imaging remains impossible even for the largest ground-based telescopes. The visitor appears as nothing more than a fuzzy star-like point of light surrounded by a faint coma of gas and dust. Size estimates depend on assumptions about the object's reflectivity, composition, and activity level, all unknown quantities for an object formed around a different star. October 3, 2025, marks a pivotal moment in interstellar visitor science. 3I Atlas will pass within 0.19 astronomical units of Mars, roughly 28 to 30 million kilometers from the red planet. This close approach offers unprecedented opportunities for detailed observations using Mars orbital missions, including ESA's ExoMars Trace Gas Orbiter, NASA's Mars Reconnaissance Orbiter, and other spacecraft positioned to study the visitor from a cosmic front row seat. Harvard astronomer Avi Loeb described the Mars encounter as a blind date between an interstellar visitor and our neighboring world. Mars Reconnaissance Orbiter's HiRIC camera, capable of resolving features as small as 30 centimeters on the Martian surface, should achieve pixel scales of roughly 30 kilometers when pointed toward 3I Atlas during closest approach. While this resolution won't reveal surface details of the visitor's nucleus, it may distinguish between a compact central condensation and more diffuse coma structure. The scientific value of these observations extends beyond simple imaging. Spectrographic measurements during the Mars flyby could reveal the chemical composition of gas escaping from the visitor's nucleus as solar heating liberates ancient volatile compounds. Expected spectral lines include CN, cyanogen, CO, carbon monoxide, and CO2, carbon dioxide, molecules that would provide direct evidence of the visitor's chemical makeup and clues about conditions in its birth stellar system. Amateur astronomers worldwide have contributed crucial observations of 3I Atlas throughout its approach. Early reports suggested faster than expected brightening as the object moved. The interstellar visitor maintains its trajectory toward the Sun, drawing ever nearer. While these initial brightness measurements need meticulous calibration and verification, the object's position in the southern celestial hemisphere provides advantages for observers in Earth's southern regions. Although northern observers can monitor it during the early morning when it ascends above their southern horizon, academic observatories persist in synchronizing observation. Initiatives through institutions such as the American Association of Variable Star Observers and the Minor Planet Center. These coordinated efforts seek to document luminosity fluctuations, tail structure transformations, and spectroscopic development. As 3I Atlas reacts to intensifying solar radiation during its sunward passage, the visitor's path through the inner solar system presents numerous observation windows, extending into early 2026. After the Mars encounter on October 3rd, 3I Atlas proceeds toward perihelion, reaching its nearest solar distance on October 29th at roughly 1.36 to 1.4 astronomical units from our star. This separation maintains it beyond Earth's orbital path, yet firmly within detection range of terrestrial telescopes and orbital observatories. December 19th represents 3EA Atlas's nearest pass to Earth at approximately 1.8 astronomical units, roughly 270 million kilometers distant. By comparison, this proximity exceeds the closest Mars can approach Earth, delivering exceptional observation conditions for both academic facilities and amateur stargazers equipped with moderate telescopes throughout late 2025 and early 2026. The visitor's conduct near perihelion may illuminate whether it adheres to conventional comet development patterns or exhibits distinctive features reflecting its interstellar heritage. Solar radiation may release volatile materials that have stayed frozen for millions of years throughout the object's voyage across interstellar voids. The subsequent gas release could generate remarkable brightness surges, tail formation, or other manifestations that differentiate interstellar wanderers from native solar system comets. Tail structure stands as one of the most captivating elements of 3 Atlas observations. Academic imagery reveals anti-sunward ion characteristics matching standard comet activity, while certain amateur astronomers document forward-directed dust formations that seem to contradict conventional comet mechanics. These seeming inconsistencies likely mirror the contrasting physics controlling dust and ion tail development rather than extraordinary phenomena. Dust tails emerge through radiation pressure the subtle yet constant force of solar photons impacting microscopic fragments released from the comet's core. These fragments trace curved paths as they yield to both solar radiation force and gravitational pull, producing the elegant curved tails apparent in most comet images. Thus, tails may seem to orient in multiple directions, depending on observation geometry and the viewer's location relative to the comet's orbital surface. Ion tails develop through completely distinct physics. Solar wind removes electrons from gas particles in the comet's atmosphere, generating charged fragments that become electromagnetically linked to magnetic field threads embedded within the solar wind. These charged fragments stream directly away from the sun along magnetic field pathways, forming the slender straight tails that shift direction as solar wind. Magnetic field alignment fluctuates. The dimensional and compositional uncertainties encompassing 3 Atlas reflect the inherent difficulties of examining objects at interplanetary separations. Even our most advanced telescopes cannot distinguish surface characteristics of objects smaller than major asteroids at distances surpassing several astronomical units. Dimensional calculations rely on luminosity readings, presumptions about surface reflective properties, and frameworks of how much illumination the object disperses toward Earth. Certain media accounts have theorized that 3-2 Atlas could span up to 15 meters across. Yet these calculations should be approached skeptically until validated through thermophysical analysis that merges brightness readings with infrared observations of thermal radiation, the object's activity intensity, measuring how much gas and dust it generates relative to its dimensions. Similarly impacts perceived brightness in ways that complicate dimensional assessments. The visitor's arrival corresponds with another magnificent celestial phenomenon that guarantees to render October 2025 an unforgettable month for sky observers globally. However, initially, we must comprehend what transpires when our suns' coronal mass discharges collide with objects that have devoted eons traversing between the stars. 3 Atlas dominates headlines as an interstellar traveler. October 2025 guarantees a second celestial marvel that might overshadow the primary attraction. Comet C 2025 R2, identified in SOHO SWAN data by citizen astronomer Vladimir Bazougi on September 11th and 12th, races toward its nearest Earth passage on October 20th and 21st, potentially achieving unaided eye visibility during identical weeks that 3 Atlas executes its Mars flyby. The identification narrative itself showcases the strength of public participation in contemporary astronomy. SOHO, the Solar and Heliospheric Observatory, perpetually surveys the sun's corona and adjacent space surroundings. Its SWAN instrument, the Solar Wind Anisotropies Instrument, charts hydrogen emissions across the heliosphere, occasionally detecting comets as they intensify and commence outgassing while nearing the inner solar system. Vladimir Bazougi, examining publicly accessible SWAN data, detected a brightening entity that corresponded with no recognized comet or asteroid. His thorough examination of numerous images validated the object's cometary character and furnished preliminary orbital computations indicating a long period comet conducting its first documented approach to the inner solar system in recorded history. Comet SWAN achieved perihelion, its nearest solar approach, on September 12, 2025, mere days following its identification. This chronology accounts for the swift brightening that originally captured Bazougi's focus. Comets characteristically brighten most dramatically as they near perihelion when escalating solar heating releases volatile materials from their cores and produces the signature atmosphere and tail formations that render them visible from Earth. The orbital arrangement benefits October observations from both hemispheres. Although southern observers initially experienced superior viewing circumstances, as October advances, The comet's orientation relative to Earth and the Sun enhances for Northern Hemisphere observers, potentially delivering outstanding viewing prospects for the greatest number of amateur astronomers and casual sky enthusiasts. Present brightness forecasts indicate comet Swan could achieve magnitude 4 to 6 during its nearest Earth passage, sufficiently bright for unaided eye detection under dark skies, though binoculars or modest telescopes would disclose considerably more detail of its atmosphere and tail configuration. These brightness projections carry considerable uncertainty because comet conduct remains famously erratic, particularly for virgin comets conducting their first documented approach to the inner solar system. The chronology establishes a flawless convergence of celestial phenomena during late October 2025. The new moon phase surrounding October 20th and 21st removes lunar interference that frequently obscures dim celestial entities. The yearly Orionid meteor display achieves peak intensity during identical nights, produced by debris from Comet Halley intersecting Earth's trajectory. Sky enthusiasts could feasibly observe a luminous comet, numerous meteors hourly, and the persistent development of 3 Atlas, all during identical optimal viewing sessions. Comet Swan's classification as a long-period solar system comet contrasts dramatically with 3 Atlas's interstellar genesis. While both entities probably contain analogous volatile materials, water ice, carbon monoxide, carbon dioxide, and diverse organic compounds, they originated in completely distinct surroundings. Comet Swan condensed from material in the peripheral zones of our native solar system, approximately 4 billion years previously, potentially spending most of its existence in the remote Oort cloud before gravitational disturbance directed it sunward. The scientific inquiries presented by each object vary correspondingly. 3. I-Atlas provides perspectives into stellar system creation processes, interstellar chemistry, and how cosmic radiation influences materials during million-year passages between stars. Comet Swan delivers information regarding circumstances in the primitive solar system, the composition and architecture of the Oort cloud, and how solar heating impacts pristine cometary materials conducting their first proximate approach to the Sun. Imaging prospects abound for both academic and amateur astronomers during October's dual comet exhibition. Wide-field cameras can encompass both objects in identical frames, recording their comparative positions, brightness, and tail configurations for assessment. Time-lapse imaging could disclose modifications in atmosphere structure, tail alignment, and comprehensive brightness as solar wind circumstances fluctuate and the object's separations from Earth and the Sun alter daily. The unpredictable character of comet brightness development introduces excitement and uncertainty to October's viewing expectations. Certain comets surpass brightness forecasts dramatically, cultivating magnificent tails and achieving magnitudes that render them unmistakable unaided eye entities, even from light-contaminated urban zones. Others disappoint, neglecting to brighten as anticipated or fragmenting under solar heating pressure in ways that reduce their visual impression. Comet Swan's brief observational record renders reliable forecasts especially challenging. Unlike periodic comets that return consistently and permit astronomers to examine their behavioral patterns across numerous appearances, virgin long-period comets like Swan present no historical foundation for their brightness development, outgassing velocities, or structural steadiness under solar heating. The capability for dramatic tail cultivation introduces visual attraction to October's comet viewing prospects. Both dust and ion tails could transform into prominent characteristics as solar wind intensity persists at heightened intensities during solar maximum circumstances. Disconnection phenomena, where coronal mass discharges several ion tails from comet cores, might become observable in actual time through telescopic observations, presenting rare perspectives of space weather mechanics in operation. Amateur comet. Observers utilize diverse methodologies to monitor brightness modifications and morphological development. Visual magnitude calculations compare comet brightness to adjacent stars of established magnitude, supplying data that academic observatories cannot acquire persistently. Imaging techniques employing digital cameras and CCD systems furnish more exact measurements while recording structural modifications in atmosphere and tail characteristics. Inquiry of whether Earth might encounter debris from Comet Swan introduces speculative interest to October's observations. If our planet's trajectory intersects the comet's dust path from previous transits through the inner solar system, we might witness a minor meteor display as fragments penetrate Earth's atmosphere. Nevertheless, such phenomena remain extremely uncertain for recently identified comets without well-established debris paths. Spectroscopic observations of both comets during October could disclose chemical resemblances and distinctions that clarify their formation chronicles. Academic observatories furnished with spectrographs can identify emission signatures from particular molecules, CN, C2, O, and H2, that specify which volatile materials are sublimating from each core under solar heating. These chemical signatures furnish direct evidence of composition and formation circumstances. Viewing arrangements for October's dual comet presentation favor observers with dark skies and unobstructed horizons. Urban light contamination substantially diminishes the detectability of dim celestial entities, rendering rural or wilderness viewing locations essential for optimal comet observation. Weather configurations during late October fluctuate considerably by geographic position, necessitating adaptable planning for successful observations. Binoculars frequently deliver superior comet viewing than telescopes for casual observers. The expansive field of vision displays the complete comet, nucleus, atmosphere, and tail in perspective, rather than magnifying minor segments that may forfeit the comprehensive visual impression. 7 by 50 or 10 by 50 binoculars constitute optimal selections, furnishing adequate light collection, capability to disclose dim details while preserving comfortable viewing angles. The convergence of two luminous comets during October 2025 presents unprecedented prospects for comparative observations. Side-by-side viewing could disclose distinctions in atmosphere coloration, tail alignment, and comprehensive structure that mirror their contrasting origins and developmental chronicles. Time-lapse imaging spanning multiple nights could record how each object reacts to shifting solar wind circumstances and viewing geometry. Academic observatories globally have synchronized observation initiatives for both objects, guaranteeing thorough coverage across numerous wavelengths of electromagnetic radiation. The Hubble Space Telescope may secure high-resolution imagery that resolves structural details impossible to identify from terrestrial observatories. Radio telescopes could identify molecular emission signatures that disclose chemical composition and temperature architecture within the expanding atmosphere zones. The safety considerations for comet observation remain minimal compared to solar or lunar eclipse viewing. Comets present no immediate threat to observers and demand no specialized filters or protective apparatus beyond standard precautions for nighttime outdoor pursuits. The principal challenges encompass locating dark viewing locations, managing weather circumstances, and sustaining equipment functionality during potentially frigid October nights. Educational prospects multiply when two magnificent comets adorn identical skies during optimal viewing circumstances. Schools, astronomy organizations, and public observatories frequently arrange specialized viewing gatherings that introduce newcomers to comet science while furnishing experienced observers with opportunities to compare objects of fundamentally contrasting origins. These gatherings cultivate scientific comprehension while honoring the marvel of cosmic phenomena visible to anyone prepared to venture outside and gaze upward. As October 2025 nears, the stage is configured for a month of unprecedented celestial intensity. An interstellar visitor threading past Mars. A long-period comet achieving peak brightness, active solar weather circumstances, and persistent aftershock sequences from Venezuelan earthquakes. The convergence of phenomena spanning scales from terrestrial seismology to interstellar astronomy establishes a chronology that contests comfortable presumptions about cosmic coincidences. However, before we investigate the deeper inquiries raised by this remarkable clustering of phenomena, we must scrutinize the patterns that human consciousness inevitably perceives when dramatic events converge. In time and space, let us assemble a chronology that encompasses the remarkable clustering of phenomena during late September and early October 2025. September 23rd, V1935. Centauri erupts to unaided eye visibility in Centaurus. September 24th, magnitude 6.2 earthquake impacts Venezuela at 2221 UTC. September 25th, the 7994 Sagittari detonates in Sagittarius. Magnitude 6.3 earthquake fractures the identical Venezuelan zone. 5.5 hours following the initial tremor. Magnitude 5.8 aftershock ensues. Late September. ENL frameworks predict coronal mass discharges traversing 3I Atlas trajectory. October 3rd, interstellar visitor flyby of Mars at 0.19 astronomical units. October 20th through 21st, comet swan, nearest approach to Earth, corresponding with new moon, an Orionid meteor shower culmination. October 29th, 3I Atlas achieves perihelion at 1.36 astronomical units from the Sun. This temporal compression of dramatic phenomena across multiple domains, stellar detonations, terrestrial earthquakes, solar weather, and interstellar visitor dynamics establishes a narrative framework that seems almost orchestrated. 2 stars detonate within days. 2 significant earthquakes fracture within hours. Solar tempests thread through space during identical weeks. An interstellar visitor approaches Mars while a solar system comet achieves peak brightness. The clustering transcends simple coincidence and approaches something resembling cosmic synchronization. Human intellects evolved to identify meaningful patterns in complex surroundings. A cognitive capability that benefited our predecessors when survival relied on recognizing subtle correlations between environmental circumstances and potential dangers or advantages. This pattern recognition framework operates spontaneously, frequently beneath conscious awareness, scanning for associations that might signify causation, even when solely correlation exists. Apophenia, the inclination to perceive meaningful patterns in random information, constitutes both a strength and a potential vulnerability of human cognition. The identical mental operations that enabled our predecessors to recognize seasonal transitions, forecast weather patterns, and identify social dynamics can similarly direct us to perceive significance in coincidental clustering of unrelated phenomena. The scientific establishment provides explicit guidance on the September-October convergence. The United States Geological Survey asserts that no validated physical mechanism connects space weather phenomena to earthquake occurrence. Decades of correlation investigations have neglected to establish dependable predictive relationships between solar intensity and seismic phenomena. Academic seismologists emphasize that earthquake prediction remains unachievable using present methodologies, whether founded on terrestrial precursors or extraterrestrial influences. Correspondingly, stellar astronomers regard novae as predictable outcomes of binary star development occurring when white dwarf stars accumulate adequate material from companion stars to initiate thermonuclear runaway. The chronology of nova eruptions adheres to stellar physics rather than terrestrial or solar system influences. V1 1935, Centurin V79, 94 Sagittari constitute standard examples of processes transpiring throughout our galaxy on a consistent basis. Solar physicists investigate coronal mass discharges as natural outcomes of magnetic field development in the sun's corona during solar maximum circumstances. These phenomena occur more regularly during peak solar intensity periods, rendering late 2025 a statistically probable time for numerous CME phenomena. The interaction between solar tempests and cometary material constitutes well-comprehended plasma physics rather than exotic phenomena. Nevertheless, recognizing establishment scientific positions doesn't necessitate dismissing the remarkable character of this temporal cluster. Occasionally, the universe arranges itself in ways that extend coincidence towards something approaching poetry, even when underlying mechanisms remain mundane. The inquiry becomes, how do we maintain space for both rigorous skepticism and appropriate wonder? The both-and methodology permits us to appreciate the statistical clustering while respecting scientific boundaries. We can recognize that twin novae achieving unaided eye brightness within days constitutes an uncommon occurrence without invoking causal associations to terrestrial earthquakes. We can acknowledge that magnitude 6 earthquakes occurring within hours in identical regions follows established patterns of stress transfer and aftershock sequences without presuming solar weather influences. We can marvel at the chronology of 3 Atlas's approach during solar maximum circumstances while comprehending that this constitutes favorable observational circumstances rather than mystical synchronization. We can celebrate the confluence of 2 luminous comets during optimal viewing circumstances without concluding that cosmic forces orchestrated the alignment for human advantage. Media chronology amplifies the everything simultaneously. Sensation through concentrated reporting and social media amplification. When numerous dramatic phenomena occur within days, information cycles and online discussions establish echo chambers that reinforce perceptions of significance. The psychological impression of simultaneous coverage can render genuinely coincidental clustering appear more meaningful than statistical. Examination would validate archaeological and historical documentation reveals that humans have perpetually sought cosmic significance in terrestrial phenomena. Ancient civilizations interpreted comets as portents, eclipses as divine displeasure, and earthquake-comet coincidences as supernatural communications. These cultural patterns endure in contemporary contexts where scientific knowledge coexists with profound psychological requirements to discover meaning in seemingly random clustering. The challenge encompasses maintaining scientific rigor while recognizing the emotional and aesthetic impression of remarkable convergences. We can appreciate the beauty of cosmic chronology without abandoning critical reasoning. We can experience wonder at the universe's occasional arrangements without presuming intentional design or concealed causation. Competing hypotheses merit simultaneous contemplation, provided we sustain clear distinctions between established science and speculative possibilities. The clustered yet unrelated interpretation rests on solid physical foundations. Stellar physics accounts for novae, plate tectonics accounts for earthquakes, solar physics accounts for coronal mass discharges, and orbital mechanics accounts for comet approaches. Each phenomenon adheres to well-comprehended natural laws operating independently. The cosmic resonance interpretation ventures into more speculative territory, indicating subtle associations between phenomena that establishment science hasn't yet recognized or comprehended. This perspective doesn't necessitate abandoning physics, but rather proposes that our present understanding may be incomplete in ways that could eventually disclose genuine correlations between seemingly unrelated domains. Both perspectives can coexist intellectually provided we sustain appropriate epistemological boundaries. Established science merits primary contemplation because it rests on extensive observational validation and successful predictive capability. Speculative hypotheses merit investigation provided they remain clearly distinguished from proven knowledge and generate testable predictions. Autumn equinox season furnishes additional context that doesn't necessitate exotic explanations. The Russell-McFarland effect establishes geometric circumstances that amplify space weather impressions during September and October, rendering this period statistically more probable to generate significant geomagnetic intensity. Seasonal patterns in earthquake occurrence have been documented in certain regions, though the mechanisms remain unclear and effects are characteristically subtle. Cultural archetypal frameworks present narrative richness without necessitating literal interpretation. Comets have symbolized transformation, upheaval, and cosmic communication across human cultures for millennia. Earthquakes constitute the solid Earth, disclosing its dynamic character. Stellar detonations demonstrate the violent beauty of cosmic development. These archetypal associations furnish powerful narrative elements that resonate with profound psychological patterns while remaining independent of physical causation. The invitation extends to viewers and readers to maintain competing hypotheses lightly, appreciating both scientific rigor and narrative wonder. We can experience the synchronistic sensation of cosmic phenomena clustering without abandoning critical reasoning. We can investigate speculative associations while sustaining respect for established physics. We can celebrate the remarkable while recognizing the probable. Perhaps the most honest methodology encompasses embracing uncertainty while remaining receptive to discovery. Science advances through careful observation, hypothesis formation, and rigorous testing rather than premature certainty regarding complex phenomena. The September-October convergence furnishes rich material for both scientific examination and imaginative investigation, provided we sustain clear distinctions between what we observe, what we hypothesize, and what we genuinely know. As we delve deeper into these inquiries, one particular speculative association merits careful scrutiny: the extensively debated possibility that space weather might influence terrestrial seismic intensity through mechanisms that remain inadequately comprehended. The concept that solar tempests might influence earthquake occurrence constitutes one of the most persistent and controversial hypotheses in Earth space science. For decades, researchers have documented statistical correlations between diverse space weather phenomena and seismic intensity. Nevertheless, no extensively accepted physical mechanism explains how electromagnetic disturbances 93 million miles distant could initiate sudden fractures in Earth's crust. The most intriguing recent hypothesis originates from researcher Stephen Burns, who proposed that reductions in solar wind density following high-velocity streams could establish a kind of electromagnetic vacuum that might subtly modify crustal stress fields. According to this framework, when dense, fast-moving solar wind suddenly yields to the sparse, slow background solar wind, the transformation in electromagnetic pressure on Earth's magnetosphere could theoretically propagate through complex coupling mechanisms to influence stress accumulation on fault systems. Physics would encompass multiple stages, each introducing uncertainty and attenuation. Initially, solar wind density fluctuations would modify the configuration and pressure of Earth's magnetosphere, the magnetic bubble that shields us from most space weather effects. Modifications in magnetospheric configuration could alter electric currents flowing through the ionosphere, Earth's electrically conductive upper atmosphere. These current fluctuations might induce electromagnetic fields that propagate into Earth's crust, where they could theoretically influence piezoelectric stress in crystalline rock formations. Stage in this proposed causal sequence encompasses effects measured in nanotesla magnetic field fluctuations or microstrain stress modifications, quantities thousands of times smaller than the stress modifications required to initiate earthquakes on fault systems that aren't already extremely proximate to failure. The theoretical coupling mechanisms exist, yet their magnitudes appear inadequate to influence seismic intensity under normal circumstances. What's genuinely established scientifically is the extensive literature of correlation assertions coupled with conspicuous absence of causal demonstration. Investigations dating back decades have documented statistical associations between solar flare intensity and earthquake occurrence, geomagnetic storm intensity, and seismic phenomenon clustering, and diverse space weather indices and regional earthquake catalogs. These correlations frequently appear statistically significant when initially documented, yet frequently neglect to replicate when tested against contrasting time periods, geographic zones, or earthquake catalogs. Publication bias complicates the literature significantly. Positive correlations between space weather and earthquakes are more probable to be submitted, accepted, and cited than null results that discover no relationship. This establishes an artificial impression of scientific consensus surrounding associations that may not exist, or may be considerably weaker than the published literature indicates. Meta-analyses attempting to synthesize numerous investigations frequently discover that effect magnitudes decrease as sample magnitudes increase and methodological rigor enhances. The United States Geological Survey's official position, validated by international seismological organizations, asserts that no reliable correlation has been demonstrated between space weather and earthquake occurrence. This conclusion rests on extensive statistical examination of global earthquake catalogs compared against comprehensive space weather databases spanning numerous solar cycles. When proper statistical controls are applied, correcting for multiple comparisons, temporal clustering, and selection bias, most documented correlations disappear or become statistically insignificant. However, certain researchers persist investigating more subtle potential associations that might operate exclusively under specific circumstances. Atmospheric pressure fluctuations associated with geomagnetic storms could theoretically modify stress on fault systems. Though these pressure modifications characteristically measure less than 1 millibar, considerably smaller than normal weather-related pressure variations. These phenomena demonstrate no evident correlation with seismic events. Electromagnetic induction presents another theoretical mechanism under consideration. Powerful geomagnetic storms have the capacity to generate electric currents within conductive substances, including subterranean water networks and mineral deposits. These generated currents could theoretically modify electrochemical reactions in fault zones, potentially influencing core pressure or rock integrity in manners that might affect earthquake timing. Once again, while the theoretical frameworks exist, the magnitudes seem inadequate to meaningfully impact well-documented seismological phenomena. Gravitational influences provide a more encouraging pathway for space-Earth interactions, although not through electromagnetic processes. Earth's tidal forces resulting from lunar and solar gravitational fluctuations demonstrably affect earthquake probability, with certain research indicating moderately increased seismic activity during maximum tidal stress periods. These gravitational influences are thoroughly understood, quantifiable, and function through recognized physical processes that directly modify stress on fault networks. Could comparable gravitational influences from alternative astronomical bodies affect seismic activity? Planetary configurations, while prevalent in certain alternative hypotheses, generate gravitational influences several orders of magnitude weaker than lunar tides. Even substantial planetary alignments produce tidal forces on Earth that are inconsequential compared to standard lunar solar tidal fluctuations. The difficulty of examining space weather-earthquake relationships lies in distinguishing authentic physical connections from statistical anomalies. Earthquake patterns follow intricate statistical distributions, including aftershock chains, geographic clustering, and temporal associations that can readily produce spurious correlations with any time-varying external factor. Space weather measurements also exhibit autocorrelation, cyclical patterns, and clustering that might create apparent connections with seismic activity through mere coincidence. Rigorous examination demands pre-registered research that defines hypotheses, temporal windows, geographic areas, and statistical approaches before data analysis. Blind examination protocols where investigators analyze earthquake records without awareness of corresponding space weather states could remove unconscious bias in data selection and interpretation. Such stringent methodologies are uncommon in published research, but critical for establishing authentic connections. What would represent persuasive evidence for space weather-earthquake relationships? Initially, the suggested mechanism would require demonstrating physical feasibility through laboratory experimentation or theoretical modeling that illustrates how electromagnetic or particle influences could substantially modify stress distributions in crystalline rock. Subsequently, statistical connections would need to exhibit predictive capability exceeding random probability when evaluated prospectively against separate datasets. Additionally, any authentic relationship would probably be context-dependent rather than universal, functioning only under specific tectonic configurations, stress conditions, or fault geometries. Universal associations affecting all seismic regions uniformly appear physically unrealistic given the enormous variations in local geology, stress distributions, and fault mechanics throughout different earthquake zones. The Venezuelan seismic sequence transpired during an interval of heightened space weather activity, contributing another observation to the prolonged correlation discussion. Nevertheless, isolated coincidences establish nothing regarding systematic connections. Venezuela occupies a tectonically dynamic zone where magnitude 6 earthquakes happen irregularly yet predictably based on plate boundary mechanics and regional stress buildup patterns. If any legitimate space weather earthquake connection exists, it would most probably be modest and context-dependent rather than pronounced and universal. The influences might appear only in fault networks already extremely near failure, where minuscule additional stress modifications could accelerate rupture timing by hours, days, or weeks rather than initiating earthquakes that would not otherwise transpire. Present seismological comprehension indicates that earthquake timing relies principally on local stress field development, fault zone characteristics, and stochastic mechanisms operating within intricate nonlinear systems. External factors, whether from space weather, atmospheric pressure, or alternative sources, probably contribute minimally compared to the prevailing tectonic forces that accumulate stress across decades and discharge it abruptly during significant ruptures. The most scientifically forthright stance recognizes both the theoretical potential and the empirical constraints. Subtle electromagnetic or gravitational interaction between space weather and seismic activity cannot be completely dismissed, but no persuasive evidence shows such relationships operate with adequate magnitude to detectably influence earthquake occurrence. Subsequent investigation should emphasize physics-oriented methodologies that recognize plausible mechanisms before pursuing statistical correlations in observational information. For pragmatic earthquake readiness and risk evaluation, space weather surveillance offers no valuable data regarding seismic threats. Construction standards, emergency protocols, and public safety strategies should continue relying on established seismological understanding about fault networks, historical earthquake sequences, and probabilistic seismic hazard evaluation rather than space weather predictions. As we examine these terrestrial relationships, an even more theoretical question emerges. Could the energy from remote stellar explosions somehow affect Earth's climate or geological mechanisms across extended time periods? The concept that stellar explosions might affect Earth's climate functions across vastly different magnitudes of energy, distance, and duration than the space weather earthquake theory we recently examined. While proximate supernova could theoretically impact our planet's atmosphere and climate across geological timescales, ordinary novae like V1935 Centauri and V7994 Sagittarius are energetically considerably weaker and astronomically more remote, rendering any immediate terrestrial consequence virtually inconceivable. Let us determine the magnitudes involved with uncompromising accuracy. A characteristic nova discharges energy equivalent to our Sun's complete output across approximately 10,000 years, roughly 10 to the 43rd joules. This magnitude sounds immense by human measures, sufficient to supply our entire civilization for billions of years at present consumption levels. Nevertheless, this energy disperses spherically outward from the explosion location, diminishing according to the inverse square principle as it traverses interstellar distances. V1935 Centauri presumably resides several thousand light-years from Earth, indicating its explosion transpired millennia before human civilization established writing, agriculture, or fixed settlements. Once this ancient stellar violence reaches our solar system, the energy intensity has reduced to magnitudes comparable to brilliant starlight magnificent to witness. Completely insignificant regarding climate, influence, or atmospheric composition, not the energy ultimately arriving at Earth from these September novae amounts to perhaps several additional photons per square meter less supplementary radiation than one would obtain from a flashlight extended at arm's distance. To establish this in climate perspective, the aggregate energy Earth receives from both novae combined throughout their complete brightening and dimming phases would prove inadequate to measurably warm a single coffee cup. Compare this with nearby supernova, which constitute authentic contenders for astronomical climate influence across geological timescales. A supernova transpiring within approximately 50 light-years of Earth could potentially transmit sufficient high-energy radiation to substantially modify atmospheric chemistry. The gamma rays and X-rays from such an explosion might eliminate considerable portions of Earth's protective ozone shield, permitting increased ultraviolet radiation to penetrate the surface and potentially initiating mass extinction episodes. Certain investigators have suggested connections between nearby supernova and historical mass extinctions. Though the evidence remains disputed and intensely debated, the late Ordovician extinction, approximately 450 million years past, coincides approximately with evidence for proximate supernova activity. However, establishing definitive causal connections across such enormous timescales demands extraordinary evidence that presently does not exist. The suggested mechanisms for supernova climate influence involve intricate atmospheric chemistry rather than straightforward thermal heating. High-energy photons from stellar explosions could fragment nitrogen and oxygen molecules in Earth's upper atmosphere, producing nitrogen oxides that catalytically eliminate ozone. Diminished ozone protection would permit more solar ultraviolet radiation to penetrate Earth's surface, potentially harming ecosystems and modifying global climate configurations through complex feedback. Processes. Cosmic ray interactions furnish another perspective. Pathway for stellar influence on terrestrial climate, though again at magnitudes and timeframes distant from the September nova occurrences. Certain theories suggest that cosmic rays' high-energy particles propelled by supernova shock fronts might affect cloud development in Earth's atmosphere by supplying condensation centers for water particles. Variations in cosmic ray intensity could theoretically modify cloud coverage and consequently global climate, though experimental support for this mechanism remains restricted and disputed. Novae might contribute negligibly to cosmic ray backgrounds across astronomical timescales, but their immediate influence on Earth's cosmic ray environment would be entirely undetectable. The cosmic ray particles propelled by V1935 Centauri and V7994 Sagittarius would demand thousands of years to cross interstellar space and arrive at our solar system, where they would be indistinguishable from the general background of galactic cosmic radiation. Media accounts frequently merge different categories of stellar explosions and their potential terrestrial effects, generating confusion regarding actual versus imagined dangers. Headlines implying that stellar explosions could influence Earth's climate characteristically fail to differentiate between nearby supernova that might produce measurable consequences across geological time and distant novae that present no realistic climate influence. This conflation contributes to broader tendencies of astronomical sensationalism that emphasizes dramatic narratives over scientific precision. The temporal association between September's stellar explosions and terrestrial earthquakes supplies abundant material for pattern recognizing minds to formulate causal explanations. However, the energy magnitudes involved render any direct connection physically implausible. The total energy that will ever arrive at Earth from both novae, combined throughout their complete observable existences, equals less than 1 second of normal sunlight striking our planet's surface. Nevertheless, the scientific investigation of stellar explosions and climate remains a legitimate and captivating research domain, provided it concentrates on plausible mechanisms functioning across appropriate timescales. The galaxy's supernova frequency, roughly 1 to 3 explosions per century, indicates that Earth periodically encounters high-energy radiation from relatively nearby stellar explosions across millions of years of geological chronicle. Isotopic evidence in geological strata sometimes preserves indicators of cosmic ray bombardment that might correspond with supernova activity. Iron-60, a radioactive isotope generated primarily in supernova explosions, has been identified in deep-sea ferromanganese deposits and ice cores, supplying direct evidence that Earth occasionally experiences enhanced cosmic ray exposure from stellar sources. These isotopic indicators offer intriguing insights into how stellar explosions might influence our planet across geological time, but they function across scales of millions of years, rather than days or months. The Iron-60 identification suggests that Earth experienced amplified cosmic ray exposure approximately 2 to 3 million years ago, possibly corresponding with supernova activity in nearby stellar groups. The question of whether such enhanced cosmic ray exposure actually influenced terrestrial climate, atmospheric chemistry, or biological development remains unresolved and actively investigated. Certain theories propose relationships between cosmic ray flux variations and ice age periods, though the mechanisms remain theoretical and the evidence inconclusive. For the September 2025 novae, any climate influence remains purely theoretical and essentially zero. These distant stellar explosions will contribute no quantifiable energy to Earth's radiation balance, modify no atmospheric chemical processes, and influence no climate parameters detectably. They constitute magnificent examples of stellar evolution and Explosion physics occurring at secure astronomical distances where we can witness and examine them without experiencing any direct consequences. The broader teaching involves maintaining perspective regarding astronomical magnitudes and the distinction between spectacular cosmic phenomena and measurable terrestrial impacts. The universe regularly generates remarkable phenomena: stellar explosions, galactic collisions, black hole mergers that produce tremendous energies, but remain too remote or too transient to meaningfully influence Earth's climate system. Our planet's climate responds principally to solar radiation fluctuations, atmospheric composition modifications, ocean circulation configurations, and volcanic activity. Terrestrial and solar system processes operating across timescales from years to millennia. While exotic astronomical influences cannot be entirely dismissed across geological timescales, they remain negligible compared to the dominant forces determining Earth's climate. Evolution. The psychological attraction of connecting distant stellar explosions to earthly phenomena reflects profound human requirements to discover meaning and pattern in apparently random occurrences. These cognitive inclinations served our ancestors effectively in identifying genuine environmental correlations, but they can also guide us to perceive significance in coincidental clustering of unrelated phenomena. As we have examined terrestrial connections to cosmic events, our focus returns to the interstellar traveler that may furnish the most direct and immediate opportunity to investigate how our solar system interacts with matter from alternative stellar regions. 3I Atlas represents considerably more than a curiosity from interstellar space. It is potentially the most sensitive natural instrument we have ever possessed for examining how our sun interacts with material formed around alternative stars. While Oumuamua departed too rapidly for comprehensive study, and Borisov remained relatively remote throughout its transit, this third interstellar visitor provides unprecedented opportunities to witness solar weather influences on matter that spent millions of years traversing between stellar systems. The trajectory alone renders 3.1 Atlas extraordinary for heliospheric research. Unlike previous interstellar objects that pursued highly inclined paths through the outer solar system, this visitor threads through the ecliptic plane where solar wind concentration, magnetic field intensity, and space weather activity attain their highest magnitudes. It is approaching during solar cycle 25 maximum circumstances, when coronal mass ejection frequency peaks and solar magnetic field complexity reaches maximum disorder. Consider comets as natural magnetometers and plasma instruments floating through space. Their ion tails furnish visible evidence of invisible magnetic field lines embedded in the solar wind. Modifications in tail direction, luminosity, and structure reveal information regarding solar wind velocity, concentration, magnetic field orientation, and the transit of shock waves or alternative disturbances. Professional space weather investigators have utilized solar system comets as remote sensors for decades, deriving quantitative measurements of space plasma conditions from telescopic observations. 3I Atlas potentially extends this capability to material with entirely different formation chronicle and chemical makeup. While solar system comets condensed from the identical primordial disk that formed our planets, this interstellar visitor carries volatiles created around a different star in a different stellar system, possibly billions of years previously. If coronal mass ejections modify its behavior, we are witnessing the first documented interaction between our sun's magnetic field and matter from another stellar region. The Mars encounter on October 3rd furnishes a unique observational configuration that ground-based telescopes cannot accomplish. ESI's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance orbiter will observe 3I Atlas from positions approximately 0.19 astronomical units distant roughly 28 million kilometers, offering viewing perspectives and resolution impossible from Earth-based observatories. Mars Reconnaissance Orbiter's high RIC camera, designed for high-resolution surface imaging, should accomplish pixel dimensions of approximately 30 kilometers when directed toward the interstellar visitor. While this resolution cannot disclose surface features of the nucleus, it may distinguish between compact central concentration and extended coma structure. More significantly, simultaneous observations from Mars orbiters and Earth-based telescopes will supply parallax, measurements that could constrain the visitor's dimensions and activity level more accurately than single viewpoint observations. Spectroscopic capabilities from Mars orbital platforms offer additional scientific merit. The ExoMars Trace Gas Orbiter carries spectrometers designed to identify trace gases in the Martian atmosphere, instruments that could potentially characterize molecular emissions from 3I Atlas during closest approach. Identification of CnCO, CO2, or alternative molecular species would furnish direct evidence of the visitor's chemical composition and how solar heating releases volatiles from interstellar ice. Ground-based observatories worldwide continue coordinating observation initiatives through the International Astronomical Union's Minor Planet Center and various professional astronomical organizations. The objective involves comprehensive multi-wavelength surveillance that tracks brightness modifications, spectroscopic development, and morphological fluctuations as 3I Atlas responds to varying solar wind conditions. During its inbound passage. Amateur astronomers contribute essential observations that professional observatories focused on numerous different targets cannot furnish continuously. Visual magnitude assessments, CCD photometry, and imaging by dedicated amateur observers provides the temporal resolution required to identify short-term variations that might correlate with specific space weather phenomena. The precedent for dramatic CME comet interactions derives from extensive observations of solar system comets, most notably the stereo satellite. Documentation of Comet Encke's tail disconnection in 2007. That occurrence demonstrated the violent reality of magnetic reconnection between solar plasma and cometary material, completely severing the ion tail in a process visible to spacecraft cameras and analyzable through plasma physics models. If comparable disconnection occurrences transpire with 3I Atlas, they could furnish unprecedented insights into how solar magnetic fields interact with interstellar material. The chemical composition distinctions between solar system and interstellar volatiles might generate different ionization configurations, magnetic coupling efficiencies, or reconnection dynamics that reveal fundamental aspects of plasma physics operating under conditions unavailable in terrestrial laboratories. Scientific inquiries extend beyond straightforward space weather interactions. 3.1 Atlas carries isotopic signatures from its birth stellar system that could disclose information regarding stellar nucleosynthesis processes, supernova enrichment configurations, and chemical evolution in alternative regions of the galaxy. Solar heating that releases these ancient volatiles furnishes our first opportunity to analyze interstellar material spectroscopically at proximate range. The object's trajectory through multiple space weather environments, from the relatively tranquil conditions of interstellar space to the intense activity near solar maximum, offers a natural experiment in how cosmic radiation and magnetic fields affect interstellar material across time. Observations might reveal whether millions of years of cosmic ray exposure have modified the visitor's chemical composition, physical structure, or volatile content compared to fresh solar system comets. Professional radio. Astronomy observations could identify molecular line emissions that reveal internal temperature structure, rotation frequencies, and outgassing configurations as solar heating penetrates into the nucleus. Very long baseline interferometry techniques might resolve structural features of the coma that indicate whether the nucleus is a single, consolidated object or a loose assemblage of smaller components held together by weak gravitational attraction. The timing of 3I Atlas observations coincides with advances in space weather monitoring and modeling capabilities that were not available during previous interstellar visitor encounters. Real-time solar wind measurements from multiple spacecraft, sophisticated magnetohydrodynamic models of CME propagation, and comprehensive ground-based monitoring networks furnish context for interpreting visitor behavior, modifications that previous generations of astronomers could not accomplish. 3I Atlas may also serve as a test scenario for planetary defense capabilities. Though it presents no collision danger to Earth, the object's trajectory, brightness evolution, and response to space weather furnish opportunities to validate telescopic detection methodologies, orbital determination techniques, and characterization capabilities that would be essential if a potentially hazardous interstellar object ever approached our planet. The broader implications of interstellar visitor science extend to astrobiology and the search for life beyond Earth. If 3I Atlas carries organic compounds or alternative prebiotic materials from its birth stellar system, spectroscopic analysis could reveal whether the chemical building blocks of life are prevalent throughout the galaxy. Such discoveries would carry profound implications for comprehending how biological complexity might emerge in alternative stellar systems. The visitor's extended observability through early 2026 ensures that scientific investigations can persist long after the initial Mars flyby excitement. Perihelion on October 29th and closest approach to Earth on December 19th furnish multiple opportunities for detailed examination as the object evolves under changing solar heating conditions. As we prepare for October's unprecedented observational opportunities, the convergence of circumstances, interstellar visitor, solar maximum conditions, advanced monitoring capabilities, and coordinated international observation campaigns creates potential for discoveries that could transform our understanding of how stellar systems interact with interstellar space. The calendar pages ahead promise revelations that may answer fundamental questions regarding our place in the cosmic neighborhood. Mark October 3rd, 21st, and 29th, 2025 on your calendars. Highlight December 19th prominently. These dates represent potential watershed moments in our comprehension of interstellar visitors, space weather interactions, and the broader cosmic neighborhood that encompasses our solar system. What transpires during these precise moments may answer questions that have perplexed astronomers since humanity initially contemplated our place among the stars. October 3rd designates 3I Atlas's closest approach to Mars at 019 astronomical units, approximately 28 million kilometers from the red planet. This represents the first occasion in documented history that an interstellar visitor will transit within the orbit of Mars. Orbiters specifically engineered to examine small bodies. ESA's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter have modified their observation schedules to capture this unprecedented encounter between technology and interstellar matter. The viewing configuration offers advantages impossible to accomplish from Earth-based observatories. Mars orbiters will observe 3I Atlas from positions that furnish different viewing perspectives, potentially resolving uncertainties regarding the visitor's dimensions, configuration, an activity level that single viewpoint observations cannot address. Simultaneous observations from Mars and Earth could supply parallax, measurements that constrain distance and physical proportions more accurately than previous interstellar. Visitor encounters permitted. Harvard. Astronomer Avi Loeb's characterization of the encounter as a blind date with Mars captures both the anticipation and uncertainty surrounding these observations. Mars. Reconnaissance Orbiter's high RISE camera should accomplish resolution scales of approximately 30 kilometers per pixel when directed toward the interstellar visitor, insufficient to disclose surface features, but potentially capable of distinguishing between compact nucleus and extended coma structure. The scientific expectations must remain pragmatic to prevent disappointment when initial results become available. Interstellar visitors appear as point sources, even to the most powerful telescopes, at ranges exceeding astronomical unit distances. The most probable outcomes involve improved constraints on dimensions, brightness evolution, and spectroscopic composition rather than dramatic resolved imagery of exotic structures or unexpected phenomena. October 20th and 21st Provis, a different category of celestial spectacle is comet C 2023-A3, Sakanshane TLAS, reaches its closest approach to Earth at approximately 0.26 to 0.27 astronomical units. The timing coincides perfectly with new moon conditions that eliminate lunar interference and the annual Orionid meteor shower peak, creating optimal dark sky conditions for comet observation. Present brightness predictions suggest Comet Sakanshane Atlas could attain magnitude 4 to 6 during closest approach, sufficiently bright for naked eye visibility under dark skies and excellent viewing through binoculars or modest telescopes. However, comet brightness predictions carry tremendous uncertainty, particularly for newly discovered long-period comets making their first recorded approach to the inner solar system. Sakanshane Atlas could surpass expectations dramatically, or disappoint observers if it fails to develop the spectacular tail structures that render comets visually memorable. The confluence of multiple celestial phenomena during late October creates unprecedented opportunities for comparative observations. Sky observers could potentially witness an interstellar visitor, a brilliant solar system comet, multiple meteors per hour from the Orionid shower, and continuing space weather effects from solar cycle 25, maximum all during the identical optimal viewing sessions under dark moon conditions. October 29th represents 3I Atlas's moment of maximum solar heating as it reaches perihelion at approximately 1.36 astronomical units from the Sun. This closest approach to our star will subject the interstellar visitor to thermal conditions that may release volatile compounds secured in its nucleus for millions of years during its passage through interstellar space. Perihelion observations could reveal whether 3I Atlas follows characteristic comet evolution patterns or displays distinctive characteristics reflecting its interstellar origins. Solar heating may generate dramatic brightness increases, spectacular tail development, or fragmentation episodes that distinguish interstellar visitors from solar system comets formed under different circumstances. The perihelion distance maintains 3I Atlas outside Earth's orbit farther from the Sun than our planet, but sufficiently close for detailed ground-based observations throughout late 2025. Professional observatories worldwide have coordinated observation campaigns to monitor brightness modifications, spectroscopic development, and morphological fluctuations as the visitor responds to peak solar heating. December 19th designates 3I Atlas's closest approach to Earth at approximately 1.8 astronomical units, roughly 270 million kilometers. For comparison, this distance is closer than Mars at its most remote point from Earth, furnishing excellent viewing conditions for both professional observatories and amateur astronomers. With modest telescopes throughout the winter months, the extended observability of 3.1 Atlas through early 2026 ensures that scientific investigations can continue long after the initial excitement of the Mars flyby and perihelion passage. Unlike Oumuamua, which departed the inner solar system too rapidly for comprehensive study, this interstellar visitor offers months of detailed observation opportunities as it evolves under changing solar heating conditions and space weather influences. What to anticipate versus what constitutes exaggeration requires careful calibration of public expectations. Comets and interstellar visitors are notoriously unpredictable objects that can surpass expectations dramatically or disappoint observers who anticipate spectacular visual displays. The most probable scenarios involve gradual brightness modifications, subtle spectroscopic development, and morphological fluctuations detectable through telescopic observations, rather than dramatic naked-eye phenomena visible to casual observers. Professional imaging may reveal structural features of coma development, tail formation, and response to solar wind variations. But these discoveries will probably manifest as scientific data rather than visually spectacular displays. The most significant results may emerge from spectroscopic analysis that reveals chemical composition, isotopic proportions, and volatile content rather than dramatic visual transformations that capture media attention. Space weather monitoring continues at elevated intensity as solar cycle 25 maintains peak activity levels through late 2025 and early 2026. The Russell-McFerrin effect during autumn equinox season enhances the probability of substantial geomagnetic activity, potentially generating spectacular auroral displays and space weather impacts on technological systems. NOAA's Space Weather Prediction Center maintains continuous surveillance of solar activity through multiple satellite systems and ground-based observatories. The Enlil model continues tracking coronal mass ejection propagation through the heliosphere, furnishing forecasts of when solar storms might interact with Earth's magnetosphere, Mars orbiters, and the trajectory of 3I Atlas. Aurora. Photographers and space weather enthusiasts should monitor SWPC alerts for G-scale geomagnetic storms, scale solar radiation events, and R-scale radio blackouts that could generate visible auroral activity at lower latitudes than characteristic quiet conditions permit. The combination of solar maximum conditions and favorable equinox geometry creates optimal prospects for dramatic space weather displays throughout October and November. Earthquake monitoring in Venezuela continues as aftershock sequences evolve, following the magnitude 6.2 and 6.3 main shocks of late September. Seismological organizations maintain continuous surveillance of regional seismic activity, though no reliable methodologies exist for predicting whether larger events might transpire in the identical region across short timescales. The complex tectonics of the Caribbean-South American plate boundary ensure that this region will continue generating earthquakes irregularly but inevitably across geological time. Construction standards, emergency preparedness systems, and public safety measures should remain founded on established seismological understanding rather than speculative connections to space weather or astronomical phenomena. NOVA monitoring continues for both V1935 Centauri and V7994 Sagittarius as these stellar explosions evolve through their characteristic brightness decline phases. Professional and amateur astronomers worldwide contribute photometry and spectroscopic Observations that reveal how nova physics unfolds across timescales of months to years following the initial thermonuclear explosion. The American Association of Variable Star Observers coordinates these monitoring efforts through standardized protocols that permit meaningful comparison of observations from different observers utilizing various equipment. The high-energy signatures identified by Fermi and Swift satellites continue furnishing insights into particle acceleration, processes operating in nova shock waves. Dust formation episodes may transpire in either nova during the coming months, generating temporary brightness declines as newly formed microscopic particles absorb and scatter the star's light. These dust dip occurrences, if they transpire, would supply additional information regarding nova ejecta, composition, and the physical conditions in expanding stellar explosion remnants. The narrative we will construct about October and beyond depends critically on separating observational results from speculative interpretation. Each phenomenon, interstellar visitor behavior, space weather activity, seismic monitoring, and nova evolution follows established physical principles that operate independently of the apparent temporal clustering that captured our attention during late September. Yet the convergence itself merits documentation and analysis as a remarkable illustration of how the universe occasionally arranges dramatic events across multiple domains during compressed time intervals. Whether this clustering represents pure coincidence, subtle physical connections we do not yet comprehend, or simply the inevitable consequence of inhabiting a dynamic cosmos, remains an unresolved question that observations may help address. Audience call to action involves appreciating these celestial events safely while maintaining realistic expectations and consulting authoritative information sources rather than sensationalized media reports or unsubstantiated claims. NASA, ESA, the Minor Planet Center, the United States Geological Survey, and NOAA's Space Weather Prediction Center furnish reliable, continuously updated information regarding ongoing developments. Amateur participation in these observations offers meaningful opportunities to contribute to scientific understanding while experiencing the wonder of cosmic phenomena firsthand. Comet photography, visual magnitude assessments, aurora observation, and earthquake reporting through established networks permit citizen scientists to participate directly in documenting this remarkable period of cosmic activity. The speculative question that accompanies all these observations involves whether the temporal clustering represents something beyond statistical coincidence. If this convergence feels unusual, and it does to numerous observers, perhaps that is because our normally separated timescales of stellar evolution, geological processes, solar activity, and interstellar visitor encounters have briefly overlapped in ways that rarely transpire within human lifespans. The promise extends beyond October's immediate observations to follow-up analysis once Mars orbiter data, perihelion spectroscopy, and extended monitoring results become available. We will analyze what actually materialized rather than forecasting what might occur, maintaining the distinction between observation and interpretation that forms this foundation of reliable scientific investigation. The final evaluation of this remarkable convergence may require years of careful analysis to separate genuine physical connections from coincidental clustering, established science from speculative association, and meaningful pattern from psychological projection. What remains certain is that we are witnessing a confluence of cosmic events that spans scales from stellar explosions to terrestrial earthquakes to interstellar visitor encounters, a reminder that we inhabit a universe far more dynamic and interconnected than our daily experience typically reveals. The acknowledgments should recognize the uncertainty inherent in all these phenomena while celebrating the human capacity to observe, measure, and seek understanding of our place in a cosmos that occasionally demonstrates its capacity to surprise, inspire, and humble us through the sheer scope of its ongoing creativity. In the end, perhaps the authentic narrative is not whether these events are cosmically connected, but that we exist during the first generation in human history, capable of detecting, monitoring, and examining such convergences across multiple domains of space and time, a perspective that would have been impossible for any previous civilization in Earth's